Hello and welcome to Sleepy Science. I'm so happy you're here. Whether you're winding down after a long day, easing into stillness under the stars, or simply looking for a soft place to rest your thoughts, you've arrived at a quiet corner of the universe, where curiosity floats gently and science hums like a lullaby. Tonight we'll drift slowly through some of the deepest, strangest, and most mind-bending ideas ever whispered by the cosmos. Ideas that ask whether space-time is real or just an illusion, whether gravity can be made of loops, whether reality is actually a hologram, and whether something like a black hole can forget or even burn the truth away. From vibrating strings that sing our universe into being, to superfluids that flow in the vacuum of nothing, to particles made purely from gravity, this journey isn't just about learning. It's about unlearning what you thought the universe was made of. Gently, we'll explore space-time that shatters and reforms, dimensions that crystallize and stretch, and questions so big that even mathematics hesitates to follow. So wherever you are, under a warm blanket, beside a softly ticking clock, or curled up in some quiet corner of the world, know that you're not alone here. This is a space for thinkers who love the feeling of not knowing, for dreamers who wonder what lies beyond equations. If this peaceful kind of wonder speaks to you, please do like the video and consider subscribing. It helps more curious minds float gently into these explorations with us. Now close your eyes, take a slow breath, and let's quietly begin our descent into the shimmering uncertainty beneath reality itself. Into a universe that may be far stranger and far more beautiful than it first appears. What if space-time is not fundamental, but emergent? Imagine blowing bubbles in your backyard, watching how they shimmer and float, but then realizing the air inside each one isn't trapped or special. It's the same air that was always there, just shaped differently for a little while, as if form itself was borrowed, not born. Now imagine the entire universe is a kind of shimmering bubble, but instead of being made of air or soap, it's made of something we take for granted every second: space and time. We move through them. We measure them. We live inside them like fish live in water. But what if space and time aren't actually the container of everything, but the result of something even deeper, something hidden underneath? This is the strange and beautiful idea behind emergent space-time. The thought that space and time aren't the starting point of reality, but the product of something more fundamental, something that doesn't look like space or time at all. Think of a video game. When you play, it looks like a world, trees, skies, hills. But all of that is just code underneath. The game world isn't real in the way your room is real. It's the outcome of patterns, rules, and bits of information flowing through a computer. And in the same way, our universe might be running on underlying rules. Ones that don't care about distance or clocks, but about relationships, entanglement, energy, and logic. If this is true, then space-time is like the screen, not the code. You see things move and change on the surface, but deep down, the real action is happening where you can't see it. This isn't just an idea from dreams or sci-fi. Physicists are starting to find clues that space and time might not be as solid as they seem. In general relativity, we see that time can speed up or slow down based on gravity. These things don't behave like bricks in a wall. They behave like emergent patterns, like heat rising from a crowd, or traffic forming on a road, or waves rippling across a pond. They're real, but they're not the building blocks. They're the shapes that come from deeper rules. In some modern theories, like quantum gravity or holographic models, space-time doesn't exist on its own. Instead, it is built from entanglement patterns, the invisible ways particles are connected. Where there's more connection, there's more space. Where connections break, space might shrink or disappear entirely. Like threads in a spider web, if you tug in one place, everything shifts. And that shift, how things relate, stretch, and pull, is what we experience as distance, direction, and flow. Even time might be nothing more than the order of how things happen. A list, not a river. Like flipping pages in a storybook, the story feels like it moves, but the pages were always still. Time may emerge from change, not the other way around. But how do we even test this? How do we know if space is real or an illusion? One clue comes from black holes, those mysterious places where gravity gets so strong that not even light can escape. Inside, space and time get twisted beyond recognition. But when physicists study black holes, especially their entropy, they find something shocking. The amount of information a black hole holds is not based on its volume, but on the area of its surface. That's like saying everything you know about your room could be stored in its walls, not its space. This is where the holographic principle enters, a theory that says our 3D world might be like a hologram, where the real data is written on a faraway 2D surface. If that's true, then space itself is an illusion, like the feeling of 3D from a flat sheet. Another clue comes from attempts to merge quantum mechanics with gravity, something that's puzzled scientists for a century. In some approaches, like loop quantum gravity or tensor networks, space emerges from tiny loops or connections that don't look like anything spatial at first. They're abstract, like numbers talking to each other. Only when enough of these loops combine in certain ways do we get something that feels like distance, shape, or geometry. It's as if the universe builds itself from meaning before it builds itself from space. Even more exciting, some physicists believe that the reason gravity exists might be because of how information is arranged, not because of some mysterious force pulling things together, but because systems naturally try to balance their internal relationships, like a stretched rubber band snapping back. This would mean that gravity isn't fundamental either. It's just what happens when space-time tries to keep its secrets consistent. And if gravity is emergent, then maybe the Big Bang wasn't the beginning of space. It was the beginning of the rules that allowed space to exist at all. It unfolds like a song, note by note, pattern by pattern, played by an orchestra of invisible rules we're only just beginning to hear. And here's the wildest part. If space and time are not fundamental, then they might not be necessary. Other kinds of worlds, other forms of physics, might exist where space is different, or doesn't exist at all. Maybe our universe is just one of many ways to arrange relationships, and we happen to evolve in one where those relationships look like stars, galaxies, motion, and memory. If we could understand the rules beneath, we might not just understand our universe, we might learn what kinds of universes are even possible. But let's bring it back to you. Right now, as you sit or lie wherever you are, feeling the weight of your body and the flow of time, realize this: the space around you might not be a container. It might be a consequence. You might not be in the universe at all. You might be part of the pattern that gives rise to space. The room, the sky, the stars, they might not exist separately from your connection to them. In the deepest sense, perhaps we don't live in space. We participate in the creation of it. And if that's true, then every moment of awareness, every act of observation, every thread of attention you send into the world might not just reflect space, it might actually weave it. You are not a small object floating in a cold void. You are a node in the great tapestry, helping space become real, one connection at a time. And maybe, just maybe, that's what the universe has been doing all along, building itself not from matter, but from meaning. Quantum foam, the chaotic foundation of space-time at the Planck scale. What if the calm, empty space around you isn't calm, or empty at all, but boiling, bubbling, and dancing wildly in a chaos, too small to see, too fast to feel, yet too real to ignore? It's easy to imagine that space is just a blank stage where everything else performs, a quiet floor where atoms spin, stars shine, and time ticks forward like a gentle metronome. But when scientists peer deep into the smallest scales of reality, far smaller than atoms, far beyond molecules, deeper than any microscope could ever dream of seeing, they find something astonishing: a foam, not of soap or water, but of quantum unpredictability. This is called quantum foam, and it's the idea that at the tiniest scales of the universe, the Planck scale, about a billionth of a billionth of a billionth of a centimeter, Space itself might not be smooth or continuous, but jittery, frothy, and unstable. Imagine zooming into a pond until each ripple becomes an ocean wave, until every wave becomes a storm. Now shrink your gaze further, until the calm of space breaks into restless fizzing, where little bits of space-time pop in and out of existence, like bubbles forming and vanishing in a pot of boiling water. That's what quantum foam is, a way of describing the wild, flickering structure of the universe's floorboards. But why would space behave like that? Why not just be empty and still? To answer that, we need to remember a strange rule from quantum physics. Even nothing isn't really nothing. In the quantum world, empty space is never truly empty. It's filled with fluctuations, teeny, random changes in energy that constantly shift and pulse. Even in a perfect vacuum, these fluctuations happen because at the smallest scales, uncertainty rules. You can't know everything about a system at once. If you try to pin down energy too precisely, time becomes fuzzy. If you try to freeze a particle in place, its momentum becomes wild. These uncertainties don't just affect particles, they affect space-time itself. And that means the fabric of reality, when looked at closely enough, wiggles like the skin of a drum that never stops vibrating. The idea of quantum foam was first suggested by John Wheeler, a brilliant physicist who believed that at the tiniest scales, space isn't made of solid blocks or smooth curves. It's made of constantly changing, ever-fluctuating twists and turns. These fluctuations are so intense, so extreme, that the very geometry of space might curl, twist, or even tear and reconnect, like knots in a piece of string. At that level, black holes might appear and disappear in the blink of an eye. Entire pockets of space might briefly fold into loops, and tiny wormholes might flash into existence before vanishing again. It's not that these things definitely happen, but in quantum mechanics, if something is allowed even for the briefest moment, it might happen. And at the Planck scale, every moment is brief. Every possibility flickers. So quantum foam isn't something we can see directly. It's a mathematical prediction, an idea born from the marriage of quantum mechanics and gravity. And this chaotic dance might explain why space behaves the way it does on larger scales. Just as the ripples of a river come from the countless moving droplets beneath, the smooth space-time we experience might come from the averaging out of all that frothy turmoil at the bottom. Like how your skin feels soft, even though it is made of countless dancing molecules. Space might feel calm, only because its madness is too small to notice. But physicists are trying to notice. Some theories suggest that the jitter of quantum foam might leave tiny fingerprints, delays in the arrival of distant light, for example, or subtle shifts in gravity. Some have even looked for signs in gamma ray bursts, brief flashes of light from faraway galaxies, to see if the photons arrive at slightly different times depending on how they've danced through quantum foam. So far, no clear signal has been found, but the search continues, with new telescopes and detectors always pushing the frontier. Why does this matter? Because understanding quantum foam might help us solve the greatest puzzle in physics: how to connect the laws of the very small with the laws of the very large. Right now, those two theories are like two languages describing the same world, but they don't quite translate. One says the universe is fuzzy and probabilistic. The other says it is curved and continuous. Quantum foam might be the missing bridge, the place where the smooth fabric of Einstein meets the unpredictable wildness of the quantum world. If we can understand this bridge, we might finally understand what space really is, and how it began. Even more surprisingly, quantum foam suggests that space-time isn't made of space and time, but of something deeper: energy patterns, entanglements, topologies, maybe even information. In some models, space emerges from the way quantum systems relate to each other. Where those relationships are dense, space becomes thick. Where they vanish, space might end. In that view, foam isn't just random chaos. It's the primal code, the first flicker of geometry before shape exists. So the next time you look at the night sky and feel the vast, silent stillness of space, remember, beneath that stillness is a furious, invisible sea. A place where the rules of reality haven't yet settled down, where space is only space because it bubbles, where nothing is ever truly nothing, and where the quiet you feel is built from noise you'll never hear. This isn't just science. It's a whisper from the roots of existence, reminding us that even the most stable things might be balanced on the edge of constant change. Maybe you are too. Symmetry breaking. How perfect balance gave birth to the universe. Imagine the entire universe sitting, perfectly still, like a blank piece of paper, before the first word is written, silent and balanced and undecided, where every direction is the same, every force is equal, and nothing yet has the courage to be different. No stars, no atoms, not even time moving forward, just an unbroken symmetry so complete that reality didn't yet know which way to lean. And now imagine something tiny, almost like a secret whisper in the silence, shift slightly out of balance, like the softest breeze nudging a spinning coin to fall on one side instead of the other. And that tiny choice, that microscopic preference, is what shattered the stillness and built everything you see, everything that exists. That is symmetry breaking. The idea that the universe was once in a perfect state of harmony where all possibilities were equal. But that perfection wasn't meant to last, and the moment it fractured, reality began. To understand how this works, picture a pencil standing perfectly upright on its tip. It's balanced, motionless, symmetrical in all directions. But it can't stay that way forever. Eventually it falls. But not because of a huge force, just the smallest nudge in any direction, and that fall picks one direction over the others, breaking the balance, breaking the symmetry. That's what scientists believe happened at the birth of the universe. At the very beginning, right after the Big Bang, the universe was incredibly hot, incredibly dense, and incredibly uniform. Every force was the same, every particle interchangeable, and time hadn't yet chosen a rhythm. But then something broke. As the universe cooled and expanded, it began to choose. Forces that were once one and the same began to separate. The strong nuclear force, the weak nuclear force, electromagnetism and gravity, all of them were once part of a single, unified force. But as the cosmic temperature dropped, like steam condensing into droplets, the universe lost its symmetry, and the forces froze into their own identities. It's as if colors that were once blended into pure white light suddenly split into rainbows, revealing the diversity that was always hidden inside. This moment of separation, when unity gives way to variety, is called spontaneous symmetry breaking. And it's one of the most powerful concepts in all of physics, because it tells us that difference comes from sameness, and structure is born from instability. Without this break, atoms could not form, particles would have no mass, galaxies wouldn't clump together, and you, sitting there, listening, would not exist. One of the most famous examples of symmetry breaking lives inside your very body, inside every atom. In the story of the Higgs field, you might have heard of the Higgs boson, sometimes called the God particle, not because it's divine, but because it gives mass to other particles. But the truth is even more elegant. The Higgs field is like a calm ocean that fills all of space, and when the early universe was perfectly symmetric, particles didn't have mass. They zipped around at the speed of light with no weight, no resistance, no identity. But when the symmetry broke, and the Higgs field settled into a non-zero value, like water freezing into ice, certain particles began to interact with it, slowing down, gaining mass, becoming real in a way they weren't before. That is symmetry breaking in action, the birth of substance from stillness. And it doesn't stop there. The imbalance between matter and antimatter, the reason you're made of atoms, instead of being annihilated into pure light, may also come from a kind of symmetry breaking. The dominance of left-handed neutrinos over right-handed ones. Another break, even the reason why the weak nuclear force seems to prefer certain directions, why it violates mirror symmetry, is a story of broken balance. Over and over, nature whispers the same lesson. Perfection is unstable, and only by breaking it does something new emerge. But why did it break at all? Why didn't the universe remain perfect forever? That's one of the deepest mysteries in science. Some theories suggest that the symmetry was never truly perfect, just an illusion of balance in the face of deeper chaos. Others think it was like a ball resting at the top of a hill, stable in theory, but in practice, doomed to fall the moment anything disturbed it. In particle physics, this is modeled through potential energy landscapes. Think of valleys and peaks, where the universe rolls from high, unstable energy into lower, stable states. And in doing so, it chooses one path among many. These choices are often irreversible. Once a symmetry is broken, it cannot be unbroken. The consequences ripple through the cosmos forever. But there's something beautiful in this too. Because without the break, without the fall, there would be no structure, no time, no gravity pulling stars together. No difference between particles, no chemical bonds, no you, no me. The act of breaking is what creates identity. Just like a blank page becomes a story only once ink disturbs its silence. The universe becomes itself only when its perfect symmetry is disturbed. And perhaps this has meaning beyond physics. Perhaps it speaks to us as people, that sometimes the most powerful beginnings come not from stability, but from disruption, that cracks can let in light, and imbalance can be the source of creativity. That to be different is not to be broken, but to be real. When you look around at the universe and see complexity, from galaxies spinning to flowers blooming to thoughts forming in your brain, remember that it all began with a perfect symmetry that chose to break. The most beautiful things often come from what isn't perfect. Maybe we do too. Black hole information paradox, the doorway to alien physics. What happens to your story when a black hole eats it? Does the universe forget? Or does it just hide the truth behind a curtain? You're never meant to pull back. This isn't just about stars being swallowed or light being trapped. It's about the deepest rule of reality breaking down. The one that says information can't just disappear. Imagine writing your name in the sand and watching a wave wash it away. It looks gone, right? But in physics, even the erased pattern is supposed to leave a trace. Every molecule of water, every grain of sand still remembers it in some way. Now imagine a black hole as the universe's biggest wave, swallowing not just sand but stars, planets, and everything written on them. And here's the puzzle. The wave doesn't leave any trace. Black holes, we thought, destroy information. And that's the paradox. It began with something strangely simple. Stephen Hawking realized in the 1970s that black holes aren't completely black. They glow, just a little. They give off something called Hawking radiation, a gentle hiss of particles from the edge of darkness. It means they're not eternal. They can shrink and fade and vanish over time, just like candles burning down. But what happens to the story they swallowed? If you toss in a piano, a book, a person, or even just one bit of information, and the black hole evaporates into nothing, where does the information go? According to quantum mechanics, information is never truly lost. Every particle, every pattern, every interaction in the universe leaves fingerprints. But according to Hawking's black hole model, all that was left behind was thermal radiation. Heat with no structure, no memory, no trace of what had fallen in. That's the paradox. General relativity says the black hole swallows and forgets. Quantum mechanics says it must remember. Both can't be true. And that's why this puzzle sits at the gateway between known physics and the physics we haven't yet dared to name. The surface of a black hole, called the event horizon, acts like a point of no return. It's not a wall or a solid shell. It's more like a border, where time and space get so twisted that escape becomes impossible. When you pass it, you're not necessarily crushed right away. You fall gently, feeling nothing strange at first, but to an outside observer, it looks like you freeze at the edge, stretched by gravity, and slowly fade from view. Now imagine that this edge isn't just a boundary. but a battleground. Because some theories now suggest the information might be stored there, like a hologram smeared across the horizon. Others believe black holes might encode what they eat into subtle patterns in their radiation, that every flicker of light escaping carries a ghost of the things it once consumed. But the problem is, hawking radiation seems purely random. It's like trying to decode a library from the heat of a bonfire. There's no structure left, or is there? This is where modern physics turns poetic and dangerous. Because if information is truly lost in black holes, then quantum theory collapses. That's not just bad news for physicists. It would mean the universe is unpredictable at its most fundamental level, that you could destroy information forever, making the past unknowable. But if information isn't lost, then black holes must be doing something we don't yet understand. Something almost magical. This paradox has led to bold ideas. Some scientists suggest that black holes are like quantum computers. Their event horizons process information in ways we can't yet model. Others propose that the inside of the black hole doesn't exist in a traditional sense at all, that the event horizon is all there is, and space beyond it is a kind of illusion. Still others believe in firewalls, that the edge of a black hole might actually incinerate anything that touches it, defying the smooth space predicted by Einstein. That would mean the very nature of black holes, and of space itself, is wrong in our current models. Another possibility, information doesn't escape the black hole. It tunnels into a different universe. Like a hidden room behind a painting, there could be new dimensions or parallel realities that black holes open up, swallowing data here and releasing it elsewhere. Some even say that black holes might be holographic projectors, converting three-dimensional data into two-dimensional codes and then back again. You don't need to believe in aliens or sci-fi for this to feel alien, because what we're seeing, if the information paradox is real, is that the universe does not follow the rules we thought it did. This is not just about physics. It's about memory, identity, and the nature of truth itself. If the universe can forget, if stories can truly be erased, then what are we? Just temporary arrangements of particles, waiting to be scrambled and lost? Or are we part of a deeper bookkeeping, where even our briefest thoughts are etched into the very structure of space? The information paradox is not solved yet, but it is shaping the future of physics. From string theory to quantum gravity, to the wildest ideas of holographic duality, every model now has to wrestle with this question: can reality be trusted to remember itself? So next time you look up at the night sky and see a black hole, invisible but massive, silent but powerful, don't think of it as empty. Think of it as the universe's secret diary, a locked one, written in a language we haven't cracked, full of everything that was ever swallowed, waiting to be read again. And maybe, just maybe, it's also a doorway, not just to new physics, but to a new understanding of what it means for something to exist and not be forgotten. The page curve, how information might leak back from black holes. What if the universe doesn't forget, but only whispers its memories back, one tiny piece at a time? What if the stories we think are lost, erased in the gravity of collapse, swallowed in the silence of time, are still there, not as pages we can read, but as faint impressions, like fingerprints on foggy glass, slowly reappearing as the air warms again? Imagine you're watching a snow globe fall to the ground and shatter into 1,000 glittering fragments. The little world it once held, its swirling magic, its quiet dream, suddenly scattered, dissolved into chaos. Now imagine somehow you had the time, the patience, and the tools to chase each of those drifting flecks of snow, to trace their paths, to study the curve of their fall and the glint of their reflection. And little by little, through the rhythm of movement, the echo of symmetry, the whisper of pattern, you begin to recreate the original story. Not perfectly, not with all its sparkle, but close enough to remember what once danced within that fragile globe. That's the quiet beauty behind a concept called the page curve. An idea from the soft backrooms of theoretical physics that might hold answers to one of the greatest mysteries of the universe. What happens to information that falls into a black hole? To understand why this idea is so hauntingly important, We need to visit the most extreme places known to physics, black holes. Not just the terrifying versions you see in movies, but the real ones, as defined by Einstein and questioned by Hawking. Those invisible wells where space folds in on itself and time becomes uncertain. Black holes don't just crush stars. They test the very laws that hold our reality together. They eat everything: planets, light, time, meaning. But the true enigma isn't what they consume. It's what, if anything, they give back for decades. We believed that nothing escaped a black hole. Toss in a novel, a life, a galaxy, and what returns is not prose or memory. It's Hawking radiation, a faint, ghostly heat, seemingly random and meaningless. This discovery by Stephen Hawking was revolutionary. It showed that black holes are not eternal. They evaporate. They glow, they fade. But it also introduced a problem. If all that comes out is heat, pure, structureless, entropy-filled heat, then the information about what went in is gone. And in the universe we know, that's not supposed to happen. Because physics, at its core, insists on a sacred rule. Information cannot be destroyed. So what happens to the story? How does the universe keep its promise? Enter Don Page, a physicist who dared to imagine a middle way. Not instant forgetting, but delayed remembering. In the 1990s, he proposed something bold and elegant. Perhaps black holes do return information, but only gradually, and only after a certain threshold is crossed. Imagine again the balloon. When it first deflates, the air hisses out, simple, unshaped, meaningless. But as the balloon shrinks, as tension builds, the air begins to squeal, to stutter, to sing. Patterns emerge, hints of what was once inside. Page suggested black holes might behave this way. Early in their evaporation, Hawking radiation looks random, but as time passes and the black hole shrinks, that radiation changes. It begins to carry structure. Tiny syllables emerge, then rhythm, then syntax. Like decoding a forgotten language, information returns in waves, faint but meaningful. This transition creates a graph, a shape, a curve. At first, the amount of retrievable information is nearly zero. Then, midway through the black hole's life, the curve begins to rise, sharply. By the end, the outgoing radiation carries nearly everything that was lost. This is the Page curve, a map of how memory might return from darkness. But Page didn't know how this happened. He could draw the curve. He could prove that quantum rules demand it. But he didn't have the mechanism. It took decades. And breakthroughs in quantum gravity, entanglement theory, and holography for the pieces to begin fitting. In recent years, physicists revisiting the edge of black holes found strange bridges forming in their equations. These weren't wormholes in the sci-fi sense, not tunnels you could travel through, but replica wormholes. Mathematical structures that allowed information to subtly link between the inside and outside of the black hole. Through these strange pathways, radiation escaping the black hole becomes quietly correlated with what remains trapped. The information isn't destroyed. It's shared, entangled, braided into the structure of reality. Think of it like a shredded letter. If you toss the pieces into the wind, you might think the message is gone. But what if the wind had a logic? What if it always carried the same fragments together? What if, with enough patience, you could learn the wind's rhythm and reassemble the message? This is what modern physics now suggests. Hawking radiation isn't just thermal noise. It's encrypted information, a song played backwards, a memory whispered through static. If you could listen long enough, understand the rules well enough, you could decode it. The Page curve represents that possibility, a hopeful slope rising from silence, showing that black holes might be not the universe's paper shredders, but its editors, fallible, indirect, but faithful. This matters not just for physics, but for philosophy. It tells us that even when things appear to vanish, their echoes remain. That meaning isn't so easily erased, that the cosmos keeps track. And why should this abstract curve matter to you, sitting here on Earth, surrounded not by event horizons, but by your own questions? regrets, and forgotten truths. Because the page curve whispers something bigger than black holes. It says that memory can survive destruction, that what seems lost can still be found. Not all at once, but piece by piece, in patience, in persistence, in presence. Maybe it's not just cosmic information that behaves this way. Maybe it's personal too. Perhaps the self you thought you lost through time, grief, change, isn't gone, but only scattered. And maybe, with enough attention, you can begin to reassemble it. Not perfectly, not the same, but meaningfully. Maybe even beautifully. In this way, physics becomes poetry. The same laws that govern stars and singularities begin to reflect the inner universe of mind and memory. And the page curve becomes more than a chart. It becomes a metaphor for healing, for return, for the slow rediscovery of self in a world that constantly threatens to erase. Black holes, in the end, may not be prisons. They may be passageways, not just through space, but through understanding, through the strange and winding path that leads from silence to signal, from absence to insight. So next time you feel something has vanished forever, remember this curve. Remember that the universe, too, once seemed to lose things it couldn't get back. And yet, the more carefully we listened, the more we found. We heard whispers where we thought there was only noise. We found code where we thought there was chaos. We discovered that even the darkest places can glow with the quiet light of memory, if we dare to look deeply enough, long enough, softly enough. Because the universe doesn't forget. It just takes its time. And maybe, so should you. Space-time entanglement. How space might emerge from quantum links. What if the universe isn't stitched together by threads of space, but by threads of connection? What if the very idea of distance is not a line measured by rulers, but the shadow left behind when two particles forget how to speak to each other? Imagine you're standing by a quiet river. You see your reflection staring back, perfect, calm, whole. But you know it's an illusion. Beneath the still surface, invisible currents churn, connecting you to something deeper. This is the suggestion of space-time entanglement. That space is not a pre-existing arena, but a whisper between entangled states. Not a container, but a chorus. A song sung between particles who still remember each other. To understand how daring this idea is, you must first let go of one of the most basic human intuitions. That space is there, like a stage built long before the actors arrive. That everything we see, stars, galaxies, trees, ourselves, is simply arranged on that pre-paved floor. But modern physics is beginning to suggest something else entirely. That the stage is improvised, not built in advance. That it only exists because of relationships, and without them, the performance and the stage vanish together. This isn't metaphor. This is emerging from some of the most advanced and mathematically rigorous theories in quantum gravity. And it's changing how we think not just about space, but about existence itself. Quantum mechanics, as strange as it already is, gave us the first clue. In this microscopic world, particles don't have positions in the usual sense. They live in fields of probability, flickering in and out of presence, behaving more like smeared possibilities than solid points. But when particles become entangled, something wild happens. No matter how far apart they move, their states remain interlinked. Measure one and you know the other. Instantly, as if the distance between them doesn't exist. Einstein called this spooky action at a distance. But the spookiness is just the beginning. Entanglement violates our classical sense of location. It suggests that particles are not truly separate, but facets of a single system. It implies that space itself may not be fundamental, but emergent. That where things are depends not on coordinates, but on whether they are connected. And here's the radical leap. What if everything that feels like space is actually the result of quantum entanglement? What if the geometry of the universe, its curves, edges, distances, is nothing more than the pattern of relationships between entangled quantum states? Imagine a vast invisible web, not made of threads, but of understanding, a network in which closeness doesn't mean meters or miles, but shared information. In this view, two particles separated by billions of light years might be right next to each other, while two others inches apart could be cosmically distant if they no longer remember each other's quantum stories. This vision is not science fiction. It's backed by frameworks like ADS over CFT correspondence, where a universe with gravity is mathematically dual to a flat system without gravity at all. The bulk spacetime emerges from quantum entanglement at the boundary. The Ryu-Takayanagi formula goes further. It literally calculates geometric areas in spacetime based on how entangled two regions of a quantum system are. It tells us that the more two systems are connected, the more tightly spaces binds them. Remove the entanglement and the bridge collapses. You're left not with separated particles, but with disconnected fragments of reality that no longer form a coherent space. This isn't just elegant math, it's a tectonic shift. It means that space may only exist where there's entanglement, that the fabric of the cosmos is woven not from points and lines, but from shared quantum histories. Remove those histories, and the world frays. And now comes the wildest implication of all. Perhaps the Big Bang didn't happen in space. It created space. Maybe, in the beginning, there was no stage, just a quantum sea of undefined possibility. And as particles began to relate, to entangle, to echo each other's states, they created geometry. They wove space into being, line by invisible line. Each entanglement was a thread. Each thread became a path, and the more complex the network, the more dimensionality emerged. If that's true, then black holes, those mysterious places where space warps beyond recognition, might be more than gravitational monsters. They might be ruptures in this network, places where entanglement gets cut, where the threads snap. And if that's what they are, then their mystery deepens. Not because they're infinitely dense, but because they are informationally silent. They're the quantum equivalent of someone forgetting all their connections. No links, no memory, no place. And perhaps death, in the deepest philosophical sense, is not the cessation of biology, but a falling out of connection, a place where entanglement ends, where consciousness stops resonating with the rest of the network. And if so, maybe life is not about occupying space, but about participating in connection. Maybe being alive means being entangled, with people, with time, with thought. This also makes consciousness itself a question of geometry. If space arises from entanglement, could awareness arise from a similar structure? Could your thoughts be near or far from each other, not in time, but in this mental space of coherence? Could trauma be a break in entanglement? Memories cast adrift. Could healing be the act of linking the scattered pieces of yourself? Could empathy, our ability to feel another's pain, be a faint quantum overlap between separate minds? None of this is proven, but the questions are being asked in serious circles, in labs, in lecture halls, in whispered late-night conversations between physicists and philosophers who have learned not to dismiss wonder too quickly. Because if entanglement builds space, then disconnection destroys it. And that gives every bond, every atom, every relationship, a new kind of weight. It means that when you feel close to someone, that closeness might not just be metaphorical, it might be physical in the deepest sense. Your minds might share a kind of geometry, a topology of understanding that we don't yet have language for, and it reframes loneliness. Maybe it's not about being far away. Maybe it's about being unentangled, unknown, not because of distance, but because of disconnection. And maybe healing, at its most profound level, is about quantum reconnection, about becoming known again, not just emotionally, but structurally. This changes how we see everything. Time, too, might not be universal. It might only flow where entanglement allows it. Maybe time doesn't move like a river, but pulses like electricity, jumping across connected nodes, flickering only where quantum links are strong. This could explain why time feels so different in different places, stretched in boredom, collapsed in panic, timeless in love. And it brings us full circle. What is space? Really, is it a distance, or a language, a memory, a relationship? Maybe, just maybe, the universe isn't a place you're in. Maybe, you're what the universe becomes when enough things connect in the right way. Maybe space lives inside you, and every time you form a bond, every time you understand, remember, empathize, you help weave the cosmos into being. Again, string theory. Vibrating dimensions beneath our reality. What if everything you've ever touched, seen, or felt, from the stars above your head to the quiet breath you're taking right now, wasn't truly made of particles at all, but of invisible, vibrating loops of energy, dancing like tiny strings in a grand cosmic symphony you can't hear but are somehow part of? Imagine just for a moment that what we call matter is simply music made solid. That quarks and electrons are not little dots, but rather the different songs a single vibrating string can play. This isn't science fiction. It's one of the boldest ideas physics has ever proposed. String theory, a framework that doesn't just explain matter, but rewrites the very foundation of reality itself. For centuries, we thought of particles as points, no size, no shape, just pure presence. Mathematical abstractions that build everything. But this point, particle idea creates problems, especially when gravity enters the stage. You see, when you try to bring together the equations that describe the very small with those that describe the very big, they simply don't get along. At high energies, or at the edge of a black hole, the math explodes into infinities, a sign that our understanding breaks down. String theory emerged as a way to fix this. Instead of particles being points, it suggests they are tiny, one-dimensional strings. So small that even the most powerful microscope could never see them. But when these strings vibrate, they behave like different particles. One vibration becomes a photon, another a graviton, another perhaps a quark. All the particles you know, and those you don't, may be nothing more than different modes of vibration on the same fundamental object. Think of it like the strings on a violin. The same string can produce many notes depending on how it vibrates. In this picture, the entire universe is music. But here's the twist. For the equations of string theory to work, the universe must have more dimensions than we observe. Not just the familiar 3 of space and 1 of time, but 10, or even 11. Where are these extra dimensions? According to theorists, they're curled up so small that we don't notice them, like the thickness of a piece of paper viewed edge on, just as an ant crawling on a garden hose could move in both directions around the hose. Even if you from a distance can only see one direction, the universe may have microscopic directions wrapped inside each point in space. These extra dimensions are where the real magic happens. The way a string vibrates depends on the shape of the space it is vibrating in. Change the geometry, and you change the laws of physics, the particles, the forces, even the constants of nature. In other words, different ways of curling up these hidden dimensions might create entirely different universes. One shape gives us electrons and gravity. Another might give rise to creatures who know nothing of light. This leads to the idea of a multiverse, not as a science fiction dream, but as a natural consequence of string theory. We may be just one bubble in a vast cosmic foam of possible realities, each shaped by the geometry of its hidden dimensions. It's humbling to think that the laws of physics, what we consider universal and fixed, might be nothing more than local notes in a grander symphony, dictated by how extra dimensions folded when the universe was born. And then comes the graviton, the hypothetical particle that carries the force of gravity. String theory naturally predicts it. It arises from a specific vibration mode of the string, without any extra assumptions. This is huge. Gravity has always resisted being included in quantum physics, but in string theory, it falls out automatically. That's why some physicists believe string theory could be the long-sought theory of everything, unifying all known forces and particles under a single elegant umbrella. But there's a cost, because string theory is so flexible, because it allows so many possible versions of reality. It's incredibly hard to test. Its predictions lie far beyond the reach of our current particle colliders. And its equations are so complex, so abstract, that even the smartest physicists sometimes get lost in their forests of math. Critics argue it's not really science, at least not yet. They say it's more like mathematical philosophy, beautiful, ambitious, but lacking in testable predictions. And they're not wrong. But maybe string theory is like a mountain in the mist, vast and real, even if we haven't found the path to climb it, after all. Many scientific ideas started as dreams. Black holes, atoms, even quantum mechanics, all were once ridiculed. Sometimes, the math leads the way before the experiments catch up. And string theory's math is undeniably compelling. It connects to other deep ideas, like quantum entanglement, holography, and emergent spacetime, in ways that hint we might be seeing only the tip of a much deeper iceberg. There's also the mysterious idea of M-theory, a possible overarching framework that unites all the different versions of string theory into one. It introduces objects beyond strings, like membranes and higher dimensional surfaces, that could be the foundation of entire universes. According to M-theory, our universe could be a three-dimensional brane, floating in a higher dimensional space, like a soap bubble drifting in a cosmic ocean. And collisions between branes might even create big bangs. It's a wild picture. But what's wild isn't always wrong. Einstein's ideas about spacetime once sounded like fantasy too. So what if, beneath all the particles and forces we see, lies something simpler? Not particles, not waves, but tiny loops of energy humming through unseen dimensions, tuning the world into being. Maybe everything is connected by a deeper rhythm, a kind of silent music that holds atoms and galaxies in the same breath. Maybe the laws of nature are not fixed notes, but flowing melodies, shaped by the spaces they move through. Maybe reality is less like a machine and more like a song. And maybe, just maybe, we are part of that song, listening not with our ears, but with our curiosity, our wonder, our quiet need to understand. In the end, string theory invites us to stop asking what the universe is made of, and start asking what kind of story it's trying to sing. Brane cosmology. Are we living on a 3D membrane in higher dimensions? Imagine waking up one morning to find that everything you've ever known, your body, your home, the sky, the stars, the memories etched into your bones, and the physics you thought were immutable, is not just suspended in space, but delicately stretched across a vast, thin, undulating sheet, a shimmering film like a cosmic curtain billowing gently in a wind you cannot feel, floating in a much larger, unseen reality that extends far beyond the limits of your perception. This world, or rather this bulk, may possess more dimensions than your senses are wired to detect, a hidden scaffolding of reality where our familiar universe is merely a ripple, a shadow, a three-dimensional sliver embedded within a higher dimensional expanse. And this isn't fantasy or poetic abstraction. It's the provocative foundation of a scientific model known as Brane cosmology, a serious extension of string theory proposing that everything you've ever observed might be confined to a brane, short for membrane, a three-dimensional hypersurface, drifting like a leaf in a multi-dimensional wind. This concept challenges not just our understanding of space, but of what it means to exist. In Brane world scenarios, all known particles, electrons, quarks, photons, the atoms in your cells, the light bouncing off your skin, are stuck to this brane, as if pinned in place by the fabric of physics itself. They cannot move into the higher dimensions of the bulk, no matter how hard they try. Only gravity, the most elusive of the fundamental forces, might have the freedom to escape, leaking out into the surrounding bulk, thinning as it stretches, which could explain why it feels so mysteriously weak compared to electromagnetism or the nuclear forces. A conundrum called the hierarchy problem that has baffled physicists for decades. If this picture is accurate, then space as we know it is a kind of illusion, a thin skin stretched across something vaster and stranger. A stage that seems complete, only because we can't see the wings beyond the curtain. Now, imagine that our brain isn't alone. Imagine an entire sea of other brains drifting in the bulk-like parallel worlds, each with its own laws of physics, its own timelines, perhaps even its own versions of stars, life, and thought. These neighboring brains might be impossibly close, just a sliver of a higher dimensional inch away, yet utterly unreachable, because the forces we rely on to sense and interact with reality can't penetrate the higher dimensional gap. And what happens if two of these brains come close? If they collide, if they graze against each other, like tectonic plates of existence? Some theories suggest that such a collision could unleash an explosion of unimaginable energy, the kind we interpret as a Big Bang, seeding a new universe from the fusion of two realities. In this view, the Big Bang wasn't the beginning of everything, but a moment of impact between two pre-existing brains, birthing space and time as we know it in a violent but beautiful flash. And if brains can ripple and flex like cosmic soap films, their motion might leave subtle fingerprints across our universe. Patterns in the cosmic microwave background, irregularities in the distribution of galaxies, whispers of memory encoded in the shape of space-time itself. But it doesn't stop there. In some models, gravity's ability to move through the bulk might allow energy to leak into our universe or out of it. Perhaps the reason we can't find enough matter to explain the motion of galaxies isn't because it's invisible, but because it's slipping sideways into a neighboring brain. Perhaps the strange acceleration of our universe's expansion, attributed to a mysterious, dark energy, is actually a symptom of interactions with unseen dimensions. What we call emptiness may be teeming with higher dimensional traffic, subtle tides that push and pull at the edges of our cosmic membrane. And black holes, those enigmatic regions where space-time curves so sharply that nothing escapes, may not simply collapse inward, but poke through the brain itself, forming bridges or funnels into the bulk, or even into other brains. A black hole might be the hole in the page of our reality, a tear that reveals a deeper chapter. Experimental evidence remains elusive, but physicists haven't given up. High-energy particle collisions, such as those performed at the Large Hadron Collider, continue to search for signs of extra dimensions, missing energy, unexpected decay paths, miniature black holes, breadcrumbs that could reveal a broader reality hiding behind the curtain. String theory, which birthed the idea of brains in the first place, requires 10 or 11 dimensions to be mathematically consistent, and brains emerge naturally within that framework as fundamental ingredients of existence, like the strings themselves, but extended across more dimensions. Just as a violin string can vibrate to produce sound, brains can ripple to create the particles and forces we observe. If string theory is the symphony of reality, then brains are its instruments, immense, resonant, multi-dimensional forms that hum the music of existence. So ask yourself, what if your entire reality, not just your body, but the space around you, is one note in that music? What if our universe is a single sheet in a cosmic book, stacked beside others? Pages that can occasionally bleed into each other, or be torn apart by forces we can't yet fathom. If so, the silence we perceive between stars may not be silence at all, but a dimensional barrier we haven't yet learned to listen through. Perhaps other civilizations exist, not light years away, but microns apart, separated not by distance, but by dimensional alignment. Perhaps consciousness, or some aspect of it, is less confined than matter, able to flicker across brains, which might explain the strange synchronicities, the unexplainable dreams, the eerie sense of presence or déjà vu that sometimes haunts human experience. And then you begin to wonder, what would it mean to move in a direction you can't point to, if up, down, left, right, forward, and back are all locked to our brain? What lies in the directions we can't name? What does it mean for something to be next to us in the bulk, but unreachable in our perception? Could there be versions of you scattered across other brains, each living slightly different lives under slightly different rules, each unaware of the others. And yet, in moments of quiet, somehow sensing the echoes, this idea transforms your understanding of presence. You're not merely in the universe, you may be on it. Everything you know, love, fear, and build is confined to this flexible, drifting surface. And yet, beyond it, possibilities stretch in directions we cannot see, a higher dimensional wilderness where the maps run out. Our universe, once thought to be all there is, becomes a local neighborhood. The cosmos becomes a layered symphony of realities. Each brain, a melody. Each collision, a crescendo. Each vibration, a verse. And so, as your thoughts drift between sleep and wonder, remember, the stars above you might be the surface lights of a floating membrane. The sky might be a ceiling woven into a film of geometry. The silence you feel might be filled with unspoken frequencies. The dimensions you move through may be only a subset of those that exist, and the meaning of here may stretch far beyond your skin. Let that thought calm you, not scare you, because it means you are part of something far vaster than you can touch. Not lost, but embedded, not confined, but rooted in a living fabric of existence that may ripple forever in every direction we have yet to name. Time crystals, matter that defies the flow of time. What if there was something in the universe that moved forever but never used energy? Something that beat like a heart, yet never got tired. Something that pulsed in a rhythm that ignored the very flow of time. Would you believe it if I told you that such a thing not only exists, but that scientists have actually created it in the lab? Time crystals. They sound like they belong in a fantasy story, like something you'd find glowing inside a wizard's staff, or buried in an alien temple. But they're real, and they break one of the oldest and most sacred rules in physics, that nothing can move forever without losing energy. And that time must always march forward, not dance in a loop. So how can this be? To understand time crystals, first imagine a normal crystal, the kind in salt, snowflakes, or diamonds. Crystals are made of atoms arranged in a repeating pattern in space, like tiles on a floor that extend infinitely in all directions. But what if a crystal didn't just repeat in space, but in time? What if, instead of standing still, the atoms pulsed back and forth in a pattern that repeated not across space, but across moments? This is the radical idea behind time crystals, that matter can be arranged not only to break the symmetry of space, by forming a repeating grid, but to break the symmetry of time itself, by choosing a beat, a rhythm, a loop. Even when time wants to flow smoothly forward like a river, in everyday physics, systems settle down. A ball stops bouncing, a pendulum slows down, a planet radiates heat. Unless you keep adding energy, motion dies out. But time crystals defy this logic. They move in perfect, repeating cycles, without consuming energy, without ever stopping, like a cosmic heartbeat that doesn't need a heart. They don't break the laws of thermodynamics, though. They simply find a loophole by living in systems that are constantly being nudged in a special way, like tapping a swing at just the right moment every time. Not to keep it going, but to trap it in a state where it wants to keep going anyway. Time crystals were first proposed by Nobel Prize-winning physicist Frank Wilczek in 2012. As a wild thought experiment, he asked, could there be a structure that repeats in time the same way a crystal repeats in space? The idea sounded impossible, even laughable, because it would mean a perpetual motion machine, and physics hates those. But it turns out, under the right conditions, in a special kind of quantum system known as a many-body localized system that is also periodically driven, this bizarre behavior actually can happen. In 2016, researchers at Princeton and later at Google and Harvard managed to build time crystal Fay-like systems using trapped ions and qubits, quantum bits, that flipped back and forth not at the speed of the laser pulses driving them, but at a slower, locked, in rhythm, meaning they chose their own beat, independent of the beat being forced on them. This self-chosen rhythm, this stubborn refusal to follow the drummer, is the essence of a time crystal. It's like bouncing a ball every second, and the ball somehow starts bouncing once every 2 seconds instead, and keeps doing that forever. But don't be fooled. This isn't a normal crystal that glows or bends light in strange ways. You can't touch it or see it easily. Time crystals are fragile, quantum systems that live at the edge of reality, and they only make sense in the world of quantum mechanics, where particles can be in many states at once, where uncertainty rules, and where cause and effect become slippery. They're like music made of atoms, a rhythm that arises from the rules of the quantum world, not from any conductor or battery. So why do time crystals matter? Because they force us to rethink time itself. Normally, physics treats time as a backdrop, a stage on which things happen. But time crystals make time part of the show. They suggest that time can be broken, sliced, and organized into patterns, just like space. And if time can be shaped like this, then what else can be done with it? Could we one day build clocks based on time crystals that never drift or degrade? Could time crystals be used in quantum computers as stable memory that resists noise and decay? Possibly, because they're incredibly resistant to certain types of errors, making them valuable for storing quantum information. But even more exciting is what they hint at: that the arrow of time, the flow of change, the very thing we believe separates the past from the future, might not be as rigid as we thought. Time crystals don't move forward. They cycle, they loop, they repeat. They introduce the idea that some systems might live outside the normal flow of time, like islands in a river where the current swirls endlessly in a circle. And this opens philosophical doors too. If time can repeat in matter, could consciousness, memory, or experience itself someday find similar loops? Could the universe, on some grand level, be shaped by repeating rhythms we haven't noticed yet? And if matter can resist the natural decay of time, does that mean there's a path to creating systems that are, in some sense, timeless, not immortal, but unchanging in a changing world? These are big questions, and time crystals are just the beginning. But what they've already shown us is remarkable: that even the most basic things we take for granted, like the one-way flow of time, or the idea that energy must always be spent to keep something moving, might be emergent, not fundamental. Just patterns that hold in most cases, but not all. Time crystals are proof that the universe still has surprises, that even now, in the 21st century, we are still discovering entirely new kinds of matter. Not just new materials, but new categories of behavior, new rules of how nature can arrange itself. And while these crystals can't be turned into energy sources or time machines, their very existence tells us that our grasp of time, perhaps the most familiar dimension, is far from complete. So next time you look at a ticking clock or feel the rush of passing days, remember, somewhere in a quiet lab, in an ultra-cold trap of ions or qubits, a time crystal is flipping, not faster, not slower, but just right, locked in a rhythm that never fades, whispering that time, like everything else, might be more flexible than it seems, and that the future of physics still pulses with rhythms we've barely begun to hear. Quantum gravity theories, bridging the gap between the very big and the very small. What if the universe were a puzzle made of two pieces that don't fit? One that describes the colossal architecture of stars and galaxies, and another that decodes the flickering behavior of particles too small to see. And no matter how clever we've become, we still can't find the seam that connects them. Picture reality as a grand story told in two conflicting languages. One speaks in the measured tones of gravity, elegance, and geometric curves, where time flows smoothly and space-time bends gently around mass, where planets follow ellipses and black holes spin like whirlpools. In velvet, the other mumbles in the bizarre tongue of quantum mechanics, where particles vanish and reappear, where uncertainty rules, and where nothing happens until you look. And then everything changes. These two languages, general relativity and quantum mechanics, are the twin monarchs of physics, both crowned by evidence, both ruling their domains with iron laws, yet forever refusing to share the same throne. Relativity governs the cosmic ballet of the very large. Quantum mechanics commands the chaotic dance of the very small. One imagines the universe as a smooth river, the other as a flickering swarm. One describes the shape of galaxies, the bending of light, the ticking of clocks under gravity's pull. The other tells us that particles can be in two places at once, or in none at all, and that probabilities, not certainties, lie at the heart of everything. But when we dare to use both together, say, to peer inside a black hole, or rewind time to the first heartbeat of the Big Bang, logic fails us. The math breaks. The reality we thought we understood crumbles. This is the problem of quantum gravity, the stubborn refusal of nature to show us how space, time, and gravity behave when quantum rules are in charge. We are missing a rulebook that combines Einstein's smooth curves with the jittery dance of quantum fields, a framework that can hold both elegance and chaos in the same breath. And so, for nearly 100 years, physicists have been chasing a dream, a single theory that unites the physics of the large with the physics of the small, the cosmic symphony with the subatomic jazz, a theory of everything, not in the sense of knowing every answer, but in the deeper sense of understanding the code behind existence, the rulebook that makes reality real. Such a theory might tell us how time emerges, what happens at the singularity of a black hole, what came before the Big Bang, if such a question even makes sense, and why the universe has the structure it does. One of the boldest early contenders for this unification was string theory, which imagines that all particles are not point-like dots, but tiny vibrating strings, each note of vibration creating a different particle, much like a violin string producing different tones. A photon is one vibration, an electron is another, and gravity, in this view, isn't separate, but just one more melody in the great string orchestra of existence. But string theory demands something radical, more dimensions, not just the 3 of space and 1 of time that we know, but 10 or even 11. Most of these extra dimensions are curled up so tightly that we never perceive them. Hidden in the small, like rooms, tucked inside the walls of the universe. These hidden dimensions are not fantasy. They're required for the math to work, for the symmetries of the strings to sing. But even string theory isn't the only voice in the chorus. Loop quantum gravity takes a wholly different path. It suggests that space itself is made of loops, woven together like threads in a cosmic fabric, creating quantized bits of area and volume. In this view, space and time are not smooth at all, but granular, made of indivisible chunks, like the digital pixels of a high-resolution screen. At the tiniest scales, far below atoms, far below protons, at the Planck length, reality is pixelated. Smoothness is an illusion of scale, like a photograph made of dots that vanish when viewed from a distance. Other approaches build reality out of triangles, like causal dynamical triangulations, where spacetime is built piece by piece, triangle by triangle, evolving like a living architecture from randomness into smooth geometry. Still others explore asymptotic safety, a theory in which gravity calms itself at high energies, refusing to spiral into mathematical chaos. And some go even deeper, suggesting that gravity itself isn't fundamental, that it emerges from something more primal, perhaps from information, or thermodynamics, or quantum entanglement. In these emergent gravity theories, space-time is a side effect, a consequence of deeper rules, just as temperature arises from the motion of molecules. Even stranger are holographic ideas, born from string theory and black hole physics, which propose that the 3-dimensional universe we live in might be a projection, a hologram of information encoded on a 2-dimensional surface at its boundary. In this view, the depth we feel, the space we move through, is not fundamental, but emergent. Real only as far as our perspective allows. And all these roads, strings, loops, triangles, emergent rules, are attempts to tell a single, coherent story, a unified narrative of how the universe works from top to bottom, from the edge of a black hole to the edge of thought. Yet, despite the beauty of these ideas, we are haunted by silence. None have been confirmed. Why? Because to test them, we must enter realms we cannot yet reach, probe inside black holes, rewind time to the first nanosecond of creation, or smash particles together with energies trillions of times greater than anything we've yet built. But clues are whispering. Gravitational waves, ripples in the fabric of space-time, have begun to show us the dynamics of the universe in new ways. The thermodynamics of black holes, how they radiate heat and encode entropy, hint that space-time is not as continuous as we thought. Quantum experiments with entangled particles, ultra-cold atoms, and microscopic masses may one day reveal gravitational effects that show the signature of quantum rules. Some hope that tiny deviations from general relativity in extreme environments or cosmic data might offer the first fingerprints of quantum gravity. The dream is that someday soon, our instruments will grow sensitive enough to hear the harmony beneath the chaos, the hidden beat that links the vast to the minuscule. The implications go beyond science. If we crack quantum gravity, we don't just complete a theory, we unveil a deeper layer of existence. Maybe space and time are not the stage, but part of the cast. Maybe gravity is not a force, but a ripple in the bookkeeping of information. Maybe the universe is not a place, but a computation, a dynamic process unfolding by rules we have only begun to glimpse. The laws we know may be low resolution shadows of laws, more real, more refined, more fundamental. To a child, this sounds like magic. To a scientist, it sounds like destiny. And perhaps they are the same thing. If the universe was never split in two, then our division of physics into big and small, smooth and jumpy, was only a misunderstanding. Like watching two instruments play different melodies, and not realizing they belong to the same song. And if we ever hear that song in full, we may discover that what we called gravity and what we called quantum mechanics were always verses of the same poem. Lines written in the geometry of existence, stanzas sung in the mathematics of being, notes strung between black holes and atoms, between the timeless and the trembling. So the next time you feel the pull of gravity or the flicker of uncertainty, remember, you are living inside a mystery that even the brightest minds have not yet solved. A cosmic duet that awaits its chorus, and somewhere, maybe just beyond the reach of our colliders and telescopes, the missing piece is humming softly, waiting to be found. Emergent gravity, when space-time is just a side effect of information flow. Have you ever wondered whether gravity, the invisible pull that keeps your feet on the ground and makes the planets dance around the sun, is truly a force, or just an illusion born from something deeper we can't yet see? Let's imagine, just for a moment, that everything you know, space, time, movement, even reality itself, is not the fundamental stuff of the universe, but a kind of side effect, a beautiful mirage that emerges from the most overlooked thing in existence: information. Not information like news headlines or trivia facts, but something far more universal, the raw bits and patterns that describe how things are, where they are, and how they change. You see, for centuries we thought gravity was a basic part of reality. Newton thought of it as a force between objects. Einstein later reimagined it as the curvature of space-time caused by mass and energy. And yet, both descriptions may be just shadows of a deeper truth. What if gravity isn't something baked into the universe, but something that emerges, like heat does from vibrating atoms or traffic patterns, do from thousands of individual drivers? This is the radical idea behind emergent gravity. The suggestion that space-time, and the gravity that shapes it, might be nothing more than the outward appearance of information arranging and flowing underneath it all. Imagine a huge school of fish swimming together in perfect formation. From far away, it looks like a single giant creature turning and twisting. But if you look closer, there's no leader, no master control. Just individual fish reacting to their neighbors. The shape is real, but it's not fundamental. It's emergent. In a similar way, emergent gravity suggests that space, time, and the force of gravity might arise from the relationships between bits of information, like tiny fish swimming in a sea of probability. The idea sounds wild, but it's rooted in serious science. A physicist named Erik Volinde proposed a version of emergent gravity, where gravity comes from something called entropic force, a force that doesn't come from a particle or field, but from the universe's tendency to organize itself toward disorder. In this view, when you move a mass, it changes the information in the universe, and the system adjusts itself. That adjustment looks like gravity, but it is not a pull. It's an informational response. It's a bit like when you press your hand on a trampoline and nearby marbles roll toward the dent, not because you're pulling them, but because the surface shape changed. The trampoline isn't pulling anything, it's just responding to your weight. Now replace the trampoline with the fabric of reality itself, and the marbles with planets and stars, and you're starting to see the picture. The concept gets even stranger when we involve something called the holographic principle. This idea suggests that everything happening inside a region of space can be described entirely by information stored on the boundary, like how a hologram appears 3D but is encoded on a two-dimensional surface. According to this, our universe might be a kind of projection. What we perceive as depth, gravity, and movement could be side effects of how data behaves at the edges. This shifts our whole understanding of physics. It says space and time aren't the theater in which particles perform, they're part of the performance itself. They're not bricks in the building. They're shadows cast by something more essential. But where does this information live, and how does it move? That's the cutting edge of research. Some scientists think the information might be stored in the quantum entanglement between particles, the invisible links that stitch reality together. Others propose that space is made from networks of connected points, and that gravity emerges from how those connections change. There's even speculation that black holes, once thought to be pure destroyers, might be the ultimate libraries, encoding vast amounts of information on their surfaces and leaking it out slowly as they evaporate. In this view, black holes aren't erasers, they're translators. All of this challenges our most basic intuitions. We're used to thinking of the universe as made of stuff, but emergent gravity flips that idea on its head. Maybe the universe isn't made of things. Maybe it's made of relationships. Maybe what we call gravity is just what it feels like when the universe tries to keep its story consistent, when it bends the rules to make sure every piece of information still fits together. For a child, you could explain it like this. Imagine you're building with invisible Lego blocks. You can't see them, but the way you place one block determines where the next can go. You keep building and building, and soon, even though you started with rules, a shape begins to form. That shape, maybe a spaceship or a castle, isn't written anywhere. It just happens because of the connections. This isn't just philosophical. It has testable implications. Volinde's model makes predictions about how galaxies behave without needing invisible dark matter. Observations are still being debated, but if proven, emergent gravity could rewrite everything we know. No more fundamental fields, no more space-time fabric. Just patterns, just flows, just logic. This raises profound questions. If space-time is not fundamental, then what is? If gravity is emergent, what else is? Could consciousness be another emergent phenomenon? Another surface of deeper informational currents? Could time itself be just a convenient illusion that keeps events from contradicting each other? We don't yet know. But the pursuit itself is reshaping science. It teaches us that what seems real might only be a useful shadow, and that behind every solid thing is a story waiting to be uncovered. So the next time you drop something and it falls, don't just thank gravity. Ask yourself, what invisible rules made it happen? What kind of universe do we live in where falling is not a force, but a message? Maybe we're not pulled down by gravity at all. Maybe we're falling into meaning, negative mass, physics on the other side of gravity. What if I told you there might be a kind of matter in the universe that doesn't fall when you drop it, but instead rises, Not because it's lighter like a balloon, but because it quite literally has the wrong kind of mass. This is not a science fiction plot twist, but the strange and serious possibility of negative mass, an idea that turns the very rules of gravity inside out and challenges our most basic understanding of how matter behaves in space. To understand it, let's start with something familiar. When you push an object, it moves in the direction you pushed. That's Newton's second law, force equals mass times acceleration. This is how the entire mechanical world behaves, from billiard balls to rocket ships. But what if you had a mass so strange that when you pushed it, it moved toward you instead? That's what negative mass would do. If you applied a force to it, it would accelerate in the opposite direction of that force. Push it and it pushes back, without needing any internal mechanism. It's not stubborn or magical, it just follows a different rulebook. That's the core of the mystery. And it raises all sorts of wild questions. Could such stuff exist in our universe? And if so, why haven't we seen it? Or have we? Could it be hiding in plain sight, misunderstood as something else entirely? Or is it simply a theoretical ghost, an artifact of equations with no physical counterpart? Negative mass is not something we find in everyday life. Drop a coffee cup and it falls. No surprise. But imagine a world where certain things, if they existed, would rise upward without buoyancy. Not because of air, but because of their very nature. It's not that they're repelled by Earth. It's that they reverse the gravitational rules. When gravity pulls, they push. And this isn't just poetic, it's mathematical. In Einstein's theory of general relativity, gravity is not a force in the traditional sense. It's the bending of space-time by energy and mass. Normally, mass bends space-time inward, like placing a bowling ball on a trampoline. But a negative mass would do the opposite. It would curve space-time upward, like lifting the trampoline from beneath. This leads to some incredibly weird effects. Picture a pair of particles, one with positive mass, the other with negative. If they're close, they would begin to chase each other endlessly. The positive mass attracts the negative one, but the negative mass repels the positive, yet is still drawn toward it by the same interaction. It's a kind of gravitational dance with no end, a self-perpetuating motion that doesn't require additional energy. That already sounds bizarre, but it gets stranger. Some physicists speculate that the accelerating expansion of the universe, often attributed to mysterious dark energy, might actually be explained by negative mass. If enough negative mass exists in the cosmos, its unusual repulsive gravity could push galaxies apart faster and faster. That would mean we're not dealing with some exotic dark force, but with a familiar concept turned upside down. But here's where things get delicate. Negative mass also introduces problems. If it existed in large quantities, it could allow violations of conservation laws or create runaway effects, where energy seems to increase endlessly. That's why many scientists remain skeptical. And yet, certain fluid systems and quantum simulations have mimicked negative mass behavior in the lab. In 2017, researchers at Washington State University cooled rubidium atoms to near absolute zero to create a Bose-Einstein condensate, a state of matter where atoms behave as a single quantum wave. Then they created conditions where the wave function acted as if it had negative mass. When pushed, it moved the wrong way. This wasn't negative mass in the pure sense, but it was a powerful analog, a glimpse into what such exotic physics might look like. Could this mean the door is open to building systems, perhaps even technologies, that use negative mass properties? The idea might sound outlandish, but remember, the concept of antimatter once sounded just as strange, and now we use it in PET scans in hospitals. The deeper you look, the more you realize that negative mass isn't just a physics curiosity. It forces us to re-examine our assumptions about the universe. What does it mean for an object to have mass? Is mass an intrinsic property, or a reflection of how an object interacts with space and time? Could there be particles that carry negative inertia? Could we one day develop propulsion systems that use negative mass to push a spacecraft forward without expelling fuel, creating a kind of gravitational slingshot. Some speculative models even suggest negative mass could stabilize wormholes, those hypothetical tunnels through space-time often imagined in science fiction. Normally, wormholes would collapse too fast for anything to travel through. But if you had negative mass to prop open the tunnel, it might remain stable. That's right. Negative mass could be the scaffolding that allows shortcuts through the cosmos. These aren't just dreams, they're mathematical possibilities, and they stem from a simple shift in perspective that not all mass needs to behave the same way. Imagine trying to teach this to a child. You could say, most things fall when you drop them, but what if you had a magic marble that didn't fall? It flew up instead, not because it was light, but because it wanted to go the opposite way of every push. That's negative mass. It's not magic, it's physics reimagined. And whether or not it turns out to be real, the idea itself expands our imagination. It challenges us to see that nature doesn't owe us intuitive behavior. Sometimes, the universe writes rules that seem backwards to us, until we realize we were standing on the wrong side of the page. So next time you drop something, and it falls, remember, that might not be the only way matter can behave. Somewhere out there, maybe in a corner of the cosmos or deep in the mathematics we've yet to unfold, there could be a place where gravity pulls and mass pushes back. And in that reversal lies a universe waiting to be discovered. Firewall hypothesis. Do black holes burn reality at the edge? What if the edge of a black hole isn't just a mysterious boundary, but a blazing wall of destruction that instantly incinerates anything that touches it, including the very fabric of what we call reality? It sounds like the stuff of science fiction, a cosmic bonfire flickering silently at the darkest reaches of space. But this unsettling idea, known as the firewall hypothesis, has emerged not from fantasy, but from the very heart of a decades-long paradox that keeps physicists awake at night. What happens to information that falls into a black hole? Let's start simple. Imagine throwing your favorite toy into a magical trash can. You expect it to vanish. Sure, but what if, years later, someone asked you exactly which toy it was, what color it was, what it was made of, and the trash can had no memory of it? That would violate a deep rule of our universe. That information can't be destroyed. Even when something burns, its information is not lost. It just spreads out in heat, light, and ash. So if you throw something into a black hole and it never comes back, not even in scattered whispers, where does its information go? This is the infamous black hole information paradox, and the firewall hypothesis is one of the most radical answers ever proposed. Traditionally, we believed that falling into a black hole would be uneventful at first. You'd pass the so-called event horizon without noticing anything strange. Like crossing an invisible border, you'd glide into the black hole's interior smoothly, while doom crept up only later, as you approached the center. But quantum mechanics, the rules that govern tiny things like particles and waves, doesn't like this peaceful picture. According to quantum theory, if black holes evaporate over time by releasing radiation, known as Hawking radiation, then somehow that radiation must carry away the information of what fell in. But here's the problem. The equations that describe black holes also say that nothing unusual happens at the horizon. You don't get fried, you just fall through. Yet, the mathematics of quantum entanglement, a delicate link between particles that can stretch across space, demands that the Hawking radiation outside the black hole be entangled with both the stuff inside and the radiation already emitted. To fix this contradiction, some physicists propose tearing the entanglement apart. But doing that is like cutting the threads that stitch space itself together, and it unleashes something horrifying. According to calculations, the breaking of these entanglements would produce a firewall, an inferno of high-energy particles right at the event horizon. Not a gentle fade into darkness, but a blazing barrier that shreds anything before it can fall in. It means your toy, your spaceship, even you, wouldn't just fall into the black hole. You'd be annihilated at its border. And not by gravity, but by quantum fury. Why does this matter? because it challenges something even deeper than physics. It challenges our trust in the smoothness of reality. In Einstein's universe, space-time is curved, but continuous. In quantum theory, it's uncertain, but calculable. The firewall screams, no, the universe might have seams that tear. This tears apart a principle known as black hole complementarity, which said that no observer ever sees a contradiction. Someone falling in experiences smoothness. Someone watching from outside sees heat and radiation. But with a firewall, that compromise collapses. There is no smooth crossing, there's only fire. This idea sparked furious debate. Some of the most brilliant minds in physics, Stephen Hawking, Leonard Susskind, Gerard Hooft, Juan Maldacena, each weighed in with arguments, counter-arguments, and alternative theories. Some insisted the firewall must exist or information will be lost. Others argued it's too radical, too ugly, a betrayal of what general relativity stands for. Could a black hole, once the silent eater of stars, actually have a skin of fire that guards its secrets? Or are we misunderstanding something even deeper, like the nature of space, or time, or entanglement itself? Interestingly, new ideas have emerged to rescue both quantum mechanics and the smoothness of the event horizon. One such idea is R equals EPR, a bold proposal that entangled particles might be connected by microscopic wormholes. If that's true, then maybe information doesn't have to pass through a firewall. Maybe it escapes through these hidden tunnels. Maybe black holes are not ends but portals. But no one knows for sure. The firewall remains a ghost, neither confirmed nor ruled out, haunting the boundary between what we understand and what we fear to admit. We don't. Now ask yourself, what if you could walk up to a black hole and hover just above its event horizon? Would you see a calm black sphere against the starry void? Or would you face a seething wall of energy so intense that space boils and time loses meaning? We don't know, because no one has ever gotten close enough to look. Not yet, but we are getting better at listening. Gravitational wave detectors, Hawking radiation models, quantum simulations, they're all trying to tell us something. And if even one clue points to the existence of firewalls, it would mean the universe has a breaking point, a zone where the familiar laws of physics snap. The horizon would no longer be a place you pass, but a place you end. In that sense, the firewall is more than a physics puzzle. It's a philosophical frontier. It asks us whether reality is truly seamless, or whether it hides scars too small or too violent for us to see. It asks whether the comfort we feel in equations and models is real, or a convenience that crumbles at the universe's most extreme edges. If space can erupt into fire, what else do we take for granted as smooth, that might be jagged, broken, or unkind beneath its surface? Perhaps firewalls are not aberrations, but signals. Perhaps they whisper that the most profound truths are not hidden in the stars, but in the paradoxes they force us to confront. So the next time you gaze into the night sky and imagine a black hole, don't think only of gravity's pull. Think of the possibility that the universe protects its deepest secrets with fire, not to burn us in cruelty, but perhaps to keep us from tearing open truths we're not yet ready to face. And in that silence, somewhere between collapse and incineration, you might find the most terrifying and beautiful thought of all. That reality, at its edge, is not a smooth curtain, but a burning question. Causal set theory, when time and cause build the universe. What if everything, every galaxy, every thought, every heartbeat, was nothing more than a single event in an invisible chain of cause and effect, and the universe itself wasn't built from space or even time, but from the raw, irreducible logic of what leads to what? Not particles, not strings, not energy fields, but causes, stitched together in an ever-growing cosmic ledger. This is the audacious starting point of causal set theory, a radical attempt to rewrite the foundations of physics by flipping the order of creation, not from space to motion, but from motion to space, not from a stage on which events unfold, but from events themselves giving birth to the stage. Imagine taking every moment in the universe, every interaction, every quantum event, every flicker of a particle, and writing it as a dot on a page. Now imagine drawing arrows from each dot to every future event it can influence, but only in one direction, forward in time. What you get is not a picture of space, but a causal network, a pure record of what happens before what. This web of connections, this raw structure of who came before whom, becomes the skeleton of the cosmos. From it, everything else, distance, dimension, duration, must emerge, not be assumed. You are no longer floating in spacetime. You are part of the structure that defines spacetime by your position in this ordered list of causality. And now, here is the twist. In causal set theory, time is fundamental, but space is not. This is the opposite of how most people picture the universe. We're used to thinking of time as a river flowing through a pre-existing terrain, a ticking clock that moves over a landscape of stars and atoms. But what if the terrain only exists because of the flow? What if the universe is a growing crystal of events, one new atom of reality added at a time, each one following the rules of what can cause what? This idea doesn't just flip our intuition, it rewires it. In causal set theory, the universe is not continuous, not smooth. It's made of discrete atoms of space-time, events that are indivisible, unbreakable, and fundamentally ordered. There is no in-between. You can't zoom in and find a blur between cause A and effect B. There is no blur. It's like digital pixels forming what appears to be a smooth picture, but underneath it is all tiny, indivisible dots. This discreteness is essential, because one of the deepest puzzles in physics is how to unify general relativity, Einstein's smooth, geometric view of space-time, with quantum mechanics, which demands discreteness, probabilities, and uncertainty. The two theories have fought for decades, unable to coexist peacefully. But what if the fight is only happening because both sides are trying to describe the same thing using different languages? Causal set theory says, forget both languages. Start from scratch. Start from events. Start from the truth that one thing happens before another, and that this order is absolute, unchangeable, and non-negotiable. From that, build your space-time, not the other way around. And here is where it gets wild. If you treat space-time as a continuous fabric, like in Einstein's equations, you run into infinities, places where the math breaks down, black holes, the Big Bang, singularities. But in a causal set, there's no such thing as infinite density or zero volume. There are only counts: how many events happened before you, how many could be influenced after. You can count the atoms of space-time. No more infinities, no more breakdowns. The singularities vanish, because you're no longer slicing something smooth into pieces. It was pieces all along. You're counting the bricks, not analyzing a mirage. And because causal sets are built from time, forward logic, they automatically encode directionality. They explain why time flows the way it does, not as a coincidence, not as a statistical fluke, but because that's how the structure is built. The arrow of time is not emergent. It's baked in. You never get loops. You never get paradoxes. You never get a cause that is also its own effect. Time is the scaffold that the universe climbs as it builds itself. But how does this help us? Practically, why should we abandon our comfortable equations for a theory built from dots and arrows? Because causal set theory could be the bridge we've been searching for. The long missing link between gravity and quantum mechanics. It gives us a way to count the building blocks of the universe, to predict where geometry should curve, to understand how gravity might arise from pure order without needing a particle to carry it. In fact, causal sets might even explain why space has dimension, why we live in 3 spatial dimensions, and not 5 or 10 or 2. Because when you look at the shape of the causal connections, the pattern of arrows, it turns out that only certain patterns naturally mimic the geometry of our universe. It is as if the dimensionality we see is not imposed, but selected, naturally, by which causal sets can persist and grow. This could explain why the universe didn't expand into something alien and chaotic, but into exactly what we see, a cosmos with the perfect balance between expansion and structure. Some researchers believe that the speed of light, that universal speed limit, is not an arbitrary cap, but a consequence of the causal set itself. If each event must respect the rule, cause comes before effect, then no influence can jump too far ahead. There is a limit to how fast anything can move through this causal network. Not because space restricts it, but because logic does. This reframes everything. Light is not the fastest thing because of physics. It's the fastest thing because of causality. You're not stuck in space because space holds you. You're held in place because the rules of cause and effect won't let you jump the queue. Even more astonishing, some variations of the theory suggest that quantum mechanics, with all its weirdness, its probabilities, its entanglement, might also emerge naturally from causal structures. If true, this would mean the universe doesn't start with randomness, but builds randomness from the top down. From the structure of how events can branch, probability becomes a shadow of causality. Entanglement becomes a map of hidden causal connections. Reality becomes a garden not of particles, but of paths. And each moment of your life, yes, yours, is a node in this vast cosmic web. You exist where you do not because of your location in space, but because of what came before you and what you are able to influence next. You are not floating in space. You are embedded in causality, and that's both humbling and electrifying. You're part of the structure of the universe. Not just a passenger, but a link in the chain, a unique point in a cosmic sentence that cannot be erased, only extended. So next time you think about the universe, don't picture a vast room. Picture a story, a sequence, a sacred order where the only truth that matters is this: some things happen before others. And from that, everything else flows. Space, time, gravity, even thought. Topology change. Can the shape of space tear and reconnect? What if space wasn't just empty? It could rip, fold, and glue itself back together, like some kind of invisible origami. What if the very structure you imagine as stable and smooth could suddenly change its shape underneath you? Not by stretching or bending like a rubber sheet, but by tearing, splitting apart, and reconnecting in entirely new configurations, as if reality itself were being restitched. This isn't fantasy. It's called topology change, and it's one of the strangest and most daring questions in theoretical physics. Topology, in simple terms, is about the shape of space. Not the size, not the curves, but the connectedness. In topology, a coffee mug and a donut are the same shape because they each have one hole. It's not about appearance, it's about how things are connected. But when we apply this to the entire universe, we're forced to confront a possibility so wild it sounds impossible: that the universe's shape, its topological skeleton, might not be fixed. It might change. Not gradually, not through erosion or expansion, but through sudden, radical restructuring. A tunnel through space might collapse. A wormhole might pinch shut. Two disconnected regions might merge. Space might sprout new branches, like roots or veins. And when that happens, the very rules of geometry and motion would flicker and shift like a dream, cracking at the edges. But here's the strange part. Our best equations in physics can't decide whether this is allowed. General relativity, Einstein's masterpiece, is built on smooth, continuous spacetime. In this picture, the fabric of the universe can bend and ripple, but it cannot tear. The topology is fixed. But quantum physics doesn't play by the same rules. In the quantum world, uncertainty reigns, and change isn't just possible. It's fundamental. And so, in some of the deepest models of quantum gravity, topology might be as fluid as time itself. This idea flips everything. Because if the topology of space can change, then where you are could be redefined. 2 points that were once miles apart might suddenly be neighbors. A loop that enclosed nothing might suddenly surround a black hole. What was once forbidden might become allowed, and vice versa. This isn't science fiction. It's a mathematical frontier. In path integrals of quantum gravity, all possible histories of the universe are considered, not just those with fixed shapes, but also those where the shape of space morphs mid-course. This means that the universe might tunnel from one topology to another, just as particles tunnel through barriers in quantum mechanics. A spherical universe could become toroidal. A disconnected space could join itself. But here is the problem. When topology changes, causality can break down. In certain configurations, it is no longer clear which events can influence others. Time might fracture. Loops of cause and effect might form, and our standard tools, our equations, our coordinates, begin to fall apart. This is why physicists tread carefully. Changing topology is like performing surgery on reality with a scalpel made of paradox. But the temptation is too strong to ignore. Because if we forbid topology change, we might be blind to the true nature of singularities, black holes, or the birth of the universe. And if we allow it, we must ask, what rules govern these changes? Are there topological conservation laws? Is there a quantum version of no tearing? Or does the universe, at its most fundamental level, play with connectivity like a child plays with blocks, building, breaking, and rearranging freely? One of the most concrete places this idea shows up is in the study of wormholes. These hypothetical tunnels through space-time require a change in topology, joining two regions that were once disconnected. In a classical picture, they're unstable or require exotic matter, but in quantum models, virtual wormholes might flicker in and out of existence all the time, like invisible stitches holding space together. If true, this could explain strange behaviors in quantum fields, non-local correlations, unexpected fluctuations, or even the holographic nature of information. The universe might be full of ghostly connections, too small to see, yet reshaping everything. Even more provocatively, some theories suggest that topology change is essential to understanding the early universe. In the chaotic moments near the Big Bang, when space-time was incredibly dense and hot, quantum fluctuations could have caused space to split, loop, or merge in countless ways. Our current universe might be just one stable configuration that emerged from that storm of topological chaos, and perhaps others still exist. Alternative shapes, unreachable but real, lying just beyond the folds of our observable cosmos. But how do we even test such an idea? It's not easy. Topology doesn't leave fingerprints like particles do. It's not a thing you can point to. It's a property of everything. Yet clues might be hiding in cosmic strings, black hole interiors, or quantum entanglement patterns. Certain gravitational wave signatures, or violations of the usual symmetry, in particle interactions might hint at past or ongoing topological transitions. The evidence is faint, but tantalizing. We might one day detect a spacequake, not a shaking of space, but a reconnection of its very structure. And then, all of physics would be rewritten, because if the shape of space is dynamic, then the laws of motion, the conservation of energy, even the flow of time might be local phenomena, shaped by global changes. Reality itself would be like a river whose banks are constantly rearranging, not just shifting positions, but gaining and losing tributaries. You might live in a universe that was once simpler, or one that's preparing to evolve again. And if space can tear, does that mean you can fall through the rip? Does consciousness require continuity of topology? If you wake up tomorrow in a newly connected space, would you notice? Would your memories survive? Would the rules you trust still apply? Or would you drift, unknowingly, through a new phase of the universe? Still made of atoms, still obeying gravity, but built on a different skeleton. These aren't idle fantasies. They're legitimate questions at the frontier of physics, and they demand humility. Because we like to think of space as the background of reality, the silent stage on which everything else plays out. But what if it's the most active character of all? What if it's the one that changes while particles merely react? What if you're not inside the universe, but woven into a changing map that forgets its previous version the moment it rewrites itself. Topology change invites us to abandon the illusion of a fixed cosmos and embrace the idea of a living, breathing geometry, a universe that isn't merely expanding or contracting, but reinventing itself at the deepest level. And perhaps, just perhaps, our very existence is possible only because of a past tear, a moment when the rules bent just enough to let complexity emerge. So when you next look at the stars, don't just wonder how far away they are. Wonder if the path to them is always the same. Wonder if the space between you and them has always been connected, or if it once wasn't, and one day might not be again. Twistor theory, a radical way to rebuild space-time from scratch. What if space-time, the very thing we think of as real, solid, and absolute, isn't the true foundation of the universe at all, but just a temporary illusion built from something far more abstract, almost dreamlike in its construction? What if time and space aren't the canvas of reality, but shadows cast by deeper, invisible shapes? Structures so strange, they don't even recognize distance or position the way we do. Welcome to Twistor theory, a mind-bending idea that suggests we've been building physics backward, trying to explain the deepest parts of the universe, using concepts that may not even be fundamental. Instead, Twistor theory proposes that we start over entirely, not with points in space or instants in time, but with twistors, entities that combine geometry, light, and quantum information into a new kind of logic. Imagine looking at reality not through snapshots of where things are and when they move, but through the pure paths that light can take. Beams, angles, trajectories, all woven into a mathematical space where position and time aren't primary ingredients. That's the world of twistors, a reality made not of things, but of relationships, not of here and now, but of directions and flows. It all began with the legendary mathematical physicist Roger Penrose, who in the 1960s dared to ask a forbidden question. What if the fabric of the universe is not a smooth, four-dimensional space-time at all, but something built from complex numbers, light rays and spin, instead of assigning coordinates to every object? Saying this particle is here, at this moment, Twistor theory says, forget positions, forget coordinates. Instead, start with light, because light is the ultimate messenger. It defines what can be seen, what can be known, what can influence. Light travels on null geodesics, paths that feel no time, only direction. And twistors are mathematical structures that describe these paths directly, bypassing the need for space-time entirely. In this new framework, the basic unit of reality is not a point, but a twistor, a bundle of information about light's trajectory and its spin. These twistors live in a weird kind of space called twistor space, an abstract realm built from complex dimensions, where geometry is encoded in how light rays intersect, diverge, and entangle. From this abstract world, the shapes of particles, fields, even entire universes emerge, like shadows cast on a wall by unseen hands. The brilliance of Twistor theory lies in its ability to describe physics without ever mentioning a when or a where. Instead, it describes how particles relate to one another through interactions that are inherently quantum, inherently geometrical, and utterly divorced from the old Newtonian grid. But it gets stranger. In twistor space, two particles colliding is not a sequence in time. It's a pattern, a matching of shapes, an overlap of trajectories in a dimensionless arena where events are not lined up, but woven together. This flips our entire intuition. In space-time, we imagine things moving, colliding, evolving. In twistor theory, nothing moves. Everything is already laid out, like a tapestry, and what we call motion is just our experience of traversing its threads. This opens the door to understanding quantum field theory in a completely new way. Feynman diagrams, which describe how particles interact through countless virtual exchanges, become simplified in twistor theory. Instead of messy calculations across dozens of steps, complex scattering amplitudes in quantum electrodynamics or quantum chromodynamics, can collapse into elegant, compact expressions, as if nature, at its core, prefers symmetry, simplicity, and light. One of the greatest successes of Twistor theory came in the early 2000s when Edward Witten, yes, the same Witten from string theory, used a variant of Twistor geometry to crack open new solutions for scattering amplitudes in quantum gauge theories. What had once required enormous computational effort became almost effortless, suggesting that the Twistor view might be closer to the universe's true operating system than our traditional picture. But this is where the philosophical implications explode. If twistors are fundamental, then space-time is emergent. It's not the stage on which reality plays. It's the illusion created by deeper symmetries. And if space-time is an illusion, then so is locality, the idea that only nearby things can affect each other. In Twistor space, closeness isn't measured in meters or seconds, but in alignment of light trajectories. This might explain why entangled particles, even if separated by light years, can act as if they're touching, because in Twistor space, they might be close. Entanglement, non-locality, quantum weirdness. They're not bugs, they're features of a deeper geometry we haven't fully grasped. Twistor theory doesn't just rewrite the rules, it questions the very fabric we've been using to write the rules on. But it's not just about abstraction or elegance. There are real hints that twistors may be the key to unifying general relativity and quantum mechanics. Our greatest challenge in physics has been to bridge the smooth, continuous spacetime of Einstein's gravity with the jittery, probabilistic world of quantum fields. Twistor theory offers a common language, a way to describe curvature, energy, and information as patterns of light trajectories in a higher dimensional space. And in doing so, it might lead to a deeper theory of quantum gravity, one where black holes, singularities, and even the origin of the universe make sense, not as places, but as geometrical events in Twistor space. But there's still much to uncover. Twistor theory is incredibly powerful, but it's also incomplete. We don't yet know how to fully recover the richness of space-time from Twistor space in all cases. The mathematics is dense, the interpretations subtle, and the connections to experiments still being drawn. Yet the promise is dazzling. A universe made not of particles in motion, but of coherent bundles of light, dancing in a realm beyond space and time. A cosmos whose laws emerge not from points and paths, but from pure relationships. And perhaps in the deepest sense, this isn't just a way to describe the universe. It's how the universe describes itself. You are not a point in space. You are a node in a cosmic network of light, spin, and symmetry. And your experience of space, time, and causality might be just your mind interpreting a deeper Twistor-based reality through a limited lens. So next time you ask where you are, maybe ask instead, how are you aligned? What direction of light are you tuned into? What angle of interaction are you experiencing? You may find that where you are is less about coordinates and more about perspective in Twistor space. And maybe, just maybe, consciousness itself is a twistor, a spinning thread of awareness weaving through the fabricless patterns of reality, leaving behind the illusion of a space-time it never truly needed. The holographic principle. Is our 3D reality just a projection? Have you ever looked at a hologram, maybe on a credit card, a museum exhibit, or a novelty sticker, and wondered how something flat could create an image that seems to rise out of the surface and float in mid-air, a shimmering, ghost-like figure appearing to occupy real space, even though you know it's just light, just illusion? Now imagine this. What if everything you see, touch, feel, and remember, every tree and star and kiss and heartbreak, even the floor under your feet, worked exactly the same way? What if the entire universe were not what it seems? Not a solid and three-dimensional reality made of stuff, but a projection, not metaphorically, a literal projection. What if everything, including your body and the stars above, emerges from information encoded on a vast, incomprehensible boundary you'll never see? a kind of cosmic screen from which reality is broadcast inward. This might sound like science fiction or a poetic thought experiment, but it's not. It's one of the most serious ideas in theoretical physics today. It's called the holographic principle, and it's challenging everything we thought we knew about space, time, matter, and what it means to be real. At the heart of the holographic principle lies a mind-bending proposal that the universe you experience in 3 dimensions is a kind of illusion, a construction that emerges from a 2-dimensional framework of information. In other words, the 3D world might not be fundamental. It might be like the image in a hologram, convincing, detailed, consistent, but ultimately just an effect, not the origin. Imagine a movie on a flat screen. It shows depth and motion, characters and worlds, but all of it comes from patterns of light on a surface. You feel immersed in the story, but the screen itself is 2-dimensional. In the case of the universe, the screen might be a vast cosmic boundary surrounding everything we know, and the story it plays is reality as we perceive it. But unlike a movie, you're not just a viewer. You are part of the projection, an actor written into the script, a pixel born from the information encoded on that boundary. But where did this radical idea come from? It begins, as many of the deepest mysteries do, with black holes. In the 1970s, physicist Jacob Bekenstein made an unsettling discovery. When matter falls into a black hole, its information, its quantum fingerprint, seems to vanish forever. But that's not supposed to happen. In quantum mechanics, information is sacred. Even if something is destroyed, its information must survive, scattered in the debris. But black holes seem to break this rule. And then Stephen Hawking complicated things even further. He showed that black holes slowly emit radiation, now called Hawking radiation, and eventually evaporate entirely. But that radiation carries no trace of what fell in. The black hole disappears. So does the information. That's a problem, a huge one. It violates the principle of unitarity, a foundation of quantum theory, which says that the evolution of a system's state must always preserve information. It's like burning a book and finding no ashes, no smoke, no heat. Nothing to hint that the book ever existed. That contradiction launched the black hole information paradox, one of the biggest open questions in physics. To resolve it, physicists began to explore radical alternatives. One idea proposed by Gerard Hooft and developed further by Leonard Susskind turned the problem inside out. What if the information never goes into the black hole at all? What if it's somehow encoded on the event horizon? The black hole's surface, like a kind of memory etched on the skin of the beast. That would mean the surface area, not the volume, determines the amount of information a black hole can contain. Normally, you'd expect information to scale with volume. The more space you have, the more room for bits. But here, surface ruled. If this is true for black holes, they reasoned, maybe it's true for the whole universe. Maybe the universe itself is a kind of black hole in reverse, a volume of space whose content is defined by its boundary. The idea gained real momentum in the late phase, when physicist Juan Maldacena made a breakthrough. He showed that in certain models of the universe, specifically those with anti-de Sitter space, the physics of gravity in a fade volume can be fully described by a quantum theory on its fade boundary. This is known as the ADS over CFT correspondence. It's as if there were 2 versions of reality, one with gravity and space, and another with only quantum fields and no gravity. Yet the 2 are mathematically equivalent. Every particle interaction in the real world corresponds perfectly to an interaction on the boundary. It's not that one is real and the other is fake. They're both complete, but one has depth, the other does not. This was the first precise, concrete example of the holographic principle in action. Since then, the implications have only deepened. If our universe is holographic, then space is not fundamental. It is emergent, a phenomenon that arises from a deeper substrate of quantum information. Your sense of up and down, your ability to move through a room, the distance between you and the moon. All of it might be the result of calculations happening on a surface you'll never see. This doesn't mean reality is fake. A hologram isn't an illusion like a magic trick. It's a different kind of reality, a derivative one, like a rainbow or a symphony. Its meaning and experience are real, but its form is built from interactions beyond its surface. The same may be true of you. Your thoughts, your body, your memories may all emerge from patterns encoded elsewhere, beyond your skin, beyond your stars, beyond your dimensions. This idea also helps resolve some deep puzzles. It explains why black holes have entropy at all, and why that entropy scales with area, not volume. It explains why quantum field theories seem so successful in describing particles, even though they say nothing about gravity, because gravity may not be a thing within the FAG world, but a reflection of deeper entanglements on the FIDE boundary. It even hints at why space seems continuous when it may actually be digital or quantized, because the underlying information is discrete, like bits on a hard drive, stitched together to create the illusion of smoothness. But the holographic principle also raises profound questions. If space is emergent, what about time? Is your sense of past and future also a projection? Is causality, what causes what, just a local rule in the holographic code? And what about consciousness? If the brain is a holographic pattern, what does that make the mind? Could awareness itself be a kind of resonance? A pattern of correlations echoing from a deeper, unseen surface? These aren't just physics questions. They're existential ones. They ask what it means to exist, to choose, to feel, if the very stage on which we live is woven from something fundamentally different. It's also worth noting that this idea echoes ancient intuitions. In many philosophies, reality is seen as a veil, a projection, a dream of a deeper truth. The holographic principle gives scientific structure to that intuition, not to diminish reality, but to elevate the mystery of its origins. You are not less real because you emerge from information. You are more precious because of it. You are not just a body in space. You are a chapter in a story written across the edge of everything. So the next time you look up at the night sky and feel that familiar sense of awe, the stars so far, the silence so deep, remember that what you're seeing might not just be out there. It might also be written on a vast, invisible surface surrounding everything, encoding every planet, every breath, every heartbeat, and every thought you've ever had. You are not watching a movie, you are made of the movie, and the screen it plays on might be the deepest, strangest, most beautiful secret the universe has ever kept. Quantum graphity, a space-time that crystallizes like matter. What if space itself wasn't always smooth and continuous, like the blank page of a notebook, but instead began as something far rougher, messy, disordered, more like a tangle of dots and lines than an elegant fabric? And only later, as the universe cooled and matured, did it crystallize into the orderly, structured space-time we live in today? Imagine, instead of thinking of space as a pre-existing background where everything unfolds, we flip the idea entirely. What if space is a kind of emergent property, something that forms from more fundamental ingredients, the way ice forms from water or crystals from molten rock? That's the wild and fascinating proposal of quantum graphity, a theory that says space-time might not be built in or eternal. It might grow and shape itself over time, the way matter goes from chaos to structure. To make sense of this, imagine the early universe not as a vast stage, but as a seething web of nodes and connections. Each node a point, each link a possible relationship, with no sense yet of near or far, left or right, up or down, just a boiling quantum soup of relations. At this deepest level, there is no distance, no geometry, not even the concept of direction. All that comes later, like the way an unshaped lump of clay slowly forms a recognizable vase. This is not just philosophical poetry. It's a concrete, testable mathematical idea born from the need to unify quantum mechanics and general relativity without contradiction, to describe how space-time itself could be an evolving network, not a fixed container. In our familiar world, space looks continuous. You can walk from here to there, stretch your arm, draw a line in the sand. But at quantum scales, continuity may be an illusion, just like a photograph looks smooth until you zoom in to see the tiny pixels. What quantum graphity suggests is that if you zoomed in far enough, far beyond what any microscope today could see, you'd discover that space isn't smooth at all. It's made of discrete elements, like points connected by switches that can be turned on or off, forming what physicists call a graph. Each connection represents whether two places are adjacent, whether information or matter can pass between them. In the early universe, every node could connect to every other, an ultra-connected, chaotic state. But as the universe cooled, just like how certain atoms in a cooling liquid begin to settle into a crystalline pattern, these connections froze into a stable structure, limiting which nodes talk to which. That's when geometry emerged, not before. In this model, space is not a thing you start with. It's a result. It condenses like ice forming from water, and with that crystallization comes something astonishing: the emergence of dimensions, of locality, of the rules that tell us how matter and energy should behave across space and time. These aren't pre-built laws. They emerge from the deeper network that underlies everything. This perspective does something powerful. It treats spacetime not as a passive backdrop, but as a dynamic player in the cosmic story. Traditionally, we've seen space as a container, something things are placed inside. But in quantum graphity, space is more like a network of relationships, like a social graph where people are nodes and friendships are connections. Only now the people are abstract points, and the friendships define the architecture of the universe. The act of connecting or disconnecting changes the very nature of space itself. You don't just move through space. You help define it by your relationships. And this graph, like idea, isn't just a metaphor. It's written into the math. The energy of the system depends on which links are active. The network can fluctuate, rearrange itself, and even heal when perturbed, just like materials in solid-state physics. In fact, the term graphity is a play on gravity and graph, reflecting how gravitational behavior could emerge from graph dynamics. The elegance here is not just in its creativity, but in how this model can mirror phenomena we actually observe in physics. For example, the way energy spreads across a graph is analogous to how particles move through space. The way clusters of connected nodes can simulate curvature resembles how mass and energy distort spacetime in Einstein's theory. And just like matter undergoes phase transitions, water to ice, steam to water, quantum graphity proposes that the universe itself underwent a spacetime phase transition, solidifying into the reality we know now. But what's even more provocative is what this theory implies about the early universe, and possibly about black holes, wormholes, and the Big Bang itself. If space-time had a phase transition, then there was a time, before space as we know it, a pre-geometric phase where no distance existed, where every point was equally connected to every other. In such a state, causality breaks down. There's no such thing as before or after, no light cone, no limitation on information travel. In a sense, the universe began as a perfect chaos, completely uniform, with every part in contact with every other. And only when this perfect symmetry broke did structure, locality, and direction emerge. That's a very different view from the classic picture of the Big Bang, starting from a tiny point in space. Instead, quantum graphity says, there was no point, there was no space, there was just an abstract web, and from that web, the space-time you walk through today slowly crystallized into being. Think about what this means. The speed of light, the rules of causality, the geometry of space. All of it might be emergent, not fundamental. They might be side effects of a deeper, more fundamental reality that doesn't look like anything we experience. And this opens up radical possibilities. Could space melt again, just as it once froze? Could gravity itself be a kind of surface tension in the geometry of this graph? Could entanglement between distant parts of the universe be traced back to their primal, all-connected state. And perhaps most mind-bending of all, quantum graphity offers a conceptual bridge between two fields that have long seemed at odds: quantum physics and general relativity. In quantum physics, everything is probabilistic, fuzzy, and governed by uncertainty. In general relativity, space-time is smooth, deterministic, and curved by mass. They clash when you try to describe extreme environments like the inside of a black hole or the first moments of the universe. But if space-time itself is emergent, maybe we've been trying to quantize the wrong thing. Maybe we don't need to force quantum rules onto space. We need to discover the quantum rules beneath space. And if space-time is a graph, then its geometry is not continuous, but built from yes, no decisions. Binary connections, like digital code. That's a revolutionary shift. It turns the analog picture of the cosmos into something digital, at its deepest layer. The same way an image on your screen is made of pixels. Perhaps the cosmos is made of spixels, space-time pixels, nodes and edges that together form the illusion of smooth space, like a digital painting forming a lifelike scene. This doesn't mean space-time isn't real, it means it's more real, in the sense that it has structure we're only beginning to glimpse. And this idea doesn't just stay on the chalkboard. It inspires real experiments and new models. Physicists explore how the properties of condensed matter systems, like superfluids, crystals, or spin networks, might mimic the behavior of space-time in graph models. Some theorists even simulate graphity, like networks on computers, watching how local rules give rise to global structure. Others try to build toy universes out of interacting bits, showing how causal structure and geometry might emerge from chaos. We haven't yet proven quantum graphity is true, but we've seen that emergence happens in many other systems. Consciousness emerges from neurons. Thermodynamics emerges from molecules. Could space-time emerge from relations? Could where and when come from the way pieces of the universe relate? If so, then quantum graphity isn't just a theory, it's a deep philosophical claim that being is secondary to relating, that reality isn't made of things, but of connections. And in a strange way, that makes the universe feel more human. Because your own life isn't just a set of objects, but a network of experiences, feelings, interactions. You're a node in your own graph. And maybe so is every star. So next time you look at the stars, or take a step through space, remember, you might be walking across a crystal, one that formed from chaos, one that keeps vibrating and shifting just beneath the level you can see. The very space between your fingers might be humming with invisible structure. Its distance is drawn not by rulers, but by relationships, by entanglements, by primal bonds that once connected everything. And just as water becomes ice, the void might have become space-time, a cosmic phase transition, whose frozen lattice became the geometry of your world. Perhaps we don't live in a void at all, but in a song, a quiet, frozen harmony of countless nodes softly clicking into place, composing the stage we call reality. Superfluid vacuum theory, a universe that flows like a liquid. What if the deepest foundation of everything you've ever seen, touched, or imagined wasn't made of particles or fields or even vibrating strings, but of something far more familiar and yet profoundly alien, a liquid, not just any liquid, but a superfluid, a substance so strange that it flows without resistance, climbs walls against gravity, and whirls forever without losing energy. Now picture this. The vacuum of space, the great cosmic emptiness between stars and galaxies, is not empty at all, but instead is a vast, invisible, superfluid ocean that carries all of existence, like a current. This isn't a science fiction metaphor. It's the radical proposal of superfluid vacuum theory, an idea that suggests our entire universe moves through, is made from, and is governed by a fluid medium, unlike anything we've ever known. Imagine space not as a void, but as a kind of cosmic riverbed through which all matter and energy gently drift, not bumping into a solid frame, but gliding through an invisible flow with its own properties, structure, and behavior. In this view, particles are not the fundamental units of the universe. Instead, they are ripples, vortices, or waves in this quantum superfluid, a gentle turbulence in the great unseen ocean of reality. And suddenly, questions about mass, inertia, and gravity take on a whole new texture, like waves moving through water rather than balls bouncing through a vacuum. Superfluid vacuum theory doesn't just offer a poetic twist on physics. It attempts to explain the deepest puzzles of the cosmos, using a principle that turns empty space into a living, breathing entity. To understand why this idea even exists, we need to revisit something modern physics has long taken for granted, that the vacuum is empty. According to traditional quantum field theory, even empty space is teeming with activity, fluctuations, virtual particles, quantum foam. But despite this theoretical richness, space is still treated like a passive backdrop, a mathematical void. Superfluid vacuum theory challenges that assumption by suggesting the vacuum isn't a stage, it's a player. It's not nothing. It's something with substance, texture, and internal rules. Just as air can carry sound or water can carry waves, this superfluid vacuum could carry the very forces and particles we experience. And here's where the theory becomes both elegant and eerie. If the vacuum is a superfluid, then what we call particles are actually excitations or disturbances in that fluid. An electron isn't a thing. It's a swirl. A photon isn't a point. It's a ripple. Gravity isn't a curvature in space. It's a change in flow. Everything we observe might be patterns in a higher order medium we don't directly perceive. This reimagining allows superfluid vacuum theory to offer solutions to problems that haunt modern physics. Why gravity is so weak. Why particles have the masses they do. Why the speed of light is constant. Why empty space isn't truly empty. Because if space is a superfluid, then all of these properties might be side effects of how that fluid behaves. Now, what makes a superfluid so special? At temperatures near absolute zero, certain fluids, like liquid helium, enter a state where they behave unlike any classical liquid. They can flow through cracks too small for atoms to pass. They can climb up and out of containers. They defy viscosity, the stickiness that slows down normal liquids. They can spin in vortexes that never decay. These are not just quirky lab results. They are hints at how quantum behavior becomes macroscopic. Superfluid vacuum theory borrows this logic and scales it up. What if the vacuum behaves like a superfluid, not just in cold labs, but everywhere, at all scales? In that case, light, gravity, and even time might be emergent phenomena from the way excitations move through this strange medium. The concept opens up new analogies. For example, if gravity is a ripple in this fluid, then massive objects like stars and black holes are sinks or whirlpools in the vacuum flow. Just as water curves around a drain, space might curve around mass, not because of some invisible geometry, but because the underlying fluid is moving, churning, adapting to what is in it. This changes how we think of the universe, not as a collection of discrete objects, but as a dynamic, continuous, fluid field of overlapping waves and eddies. What's even more compelling is how this theory could explain the existence and properties of dark energy and dark matter, the mysterious components that make up over of the universe's content. In standard cosmology, these are unexplained anomalies. Dark energy drives cosmic acceleration. Dark matter pulls galaxies together. But what if both are simply manifestations of the superfluid vacuum itself? In superfluid vacuum theory, dark matter might not be particles at all, but a specific configuration of the vacuum fluid, a dense clustering, or a kind of topological knot. Dark energy, on the other hand, could be the natural pressure or tension of the superfluid stretching outwards, creating the illusion of expansion. This means that by tweaking the properties of the vacuum fluid, its compressibility, viscosity, or flow behavior, we could, in principle, simulate or explain the large-scale behavior of the cosmos. Superfluid vacuum theory doesn't rely on new invisible particles. Instead, it gives existing observations a new interpretation through the lens of hydrodynamics and quantum coherence. The cosmos, then, isn't made of invisible bricks. It's sculpted from currents. This liquid view of the universe also offers a new way of understanding the speed of light, not as a cosmic speed limit, but as the natural speed at which ripples travel through the vacuum superfluid. Just like sound has a speed based on the properties of air, or water waves move at speeds determined by depth and gravity, light speed could be the default velocity of wave propagation in the quantum fluid. This could explain why it is constant everywhere and why it plays such a central role in the structure of spacetime. It might even suggest that in denser or more turbulent regions of the superfluid vacuum, this speed could subtly vary, leading to new predictions and insights about how light behaves near massive bodies or during cosmic events like inflation. Even the phenomenon of inertia, the resistance objects show to being moved, could be understood in fluid terms, in superfluid vacuum theory. Inertia is not a property of matter alone. It's an interaction with the medium, just like moving your hand through water creates drag and flow patterns. Moving through the vacuum superfluid could create resistance, giving mass to otherwise massless particles, and defining how they respond to forces. Of course, a radical idea like this needs more than poetry. It needs math, models, and experiments, and researchers working on superfluid vacuum theory are building those, crafting analogues from condensed matter physics, hydrodynamics, and quantum theory. They simulate how vortices in a superfluid could mimic particle behavior. They explore how changes in the vacuum's properties could alter spacetime curvature. They model how gravity might emerge, not from geometry, but from pressure gradients in a quantum fluid. And as strange as this sounds, these aren't just theoretical exercises. Laboratory experiments with Bose-Feinstein condensates, states of matter where particles act as a single coherent wave, have shown behaviors eerily similar to what superfluid vacuum theory predicts. In some setups, sound waves in these condensates mimic black holes, horizons, and even Hawking radiation. These analog spacetimes don't prove superfluid vacuum theory, but they show that reality might have more in common with fluid dynamics than classical physics ever admitted. What makes superfluid vacuum theory so captivating is not just its scientific audacity, but its philosophical implications. If the universe is a fluid, then it's not made of things. It's made of flows. It's not a place where stuff happens. It is the happening. Everything you are, everything you see, could be not a solid object, but a standing wave in an endless sea. This invites a completely new way of looking at existence, not as something built, but as something in motion, something alive, something constantly changing. It collapses the boundary between object and environment, between thing and space. You aren't separate from the vacuum. You are an expression of it, a stable ripple in a dancing fluid that stretches across time. It reframes existence from being about presence to being about persistence, about movement that lasts. Even consciousness, some speculate, might emerge from patterns in this fluid, just as complex behavior emerges from turbulent flows. While these are speculative frontiers, they show just how deeply superfluid vacuum theory reorients our understanding, not just of physics, but of being. So next time you gaze up at the night sky, or feel the silence between words, try to imagine the unseen ocean beneath it all, not a void, but a subtle tide, an invisible stream flowing through everything, carrying light, birthing gravity, holding galaxies in orbit, a universe not suspended in space, but made of space in motion, a cosmos not ticking like a clock, but humming like a current. Maybe everything is not built from particles, but from pulses. Not solid, but sung, not drawn, but danced. And maybe you too are part of that great flow, moving gently, moment by moment, in the quiet superfluid we call existence. Loop quantum gravity, a universe made of quantized space loops. What if space itself wasn't infinitely smooth and continuous, but made of loops, tiny, discrete, indivisible units forming a woven fabric, a quantum tapestry beneath all of reality, not loops of thread, but loops of space itself, tangled into networks, so minuscule yet so essential, they define the very shape of existence. Imagine peeling back the familiar canvas of stars and motion to find what we thought was seamless is actually granular, stitched together by quantum knots. This is the audacious vision of loop quantum gravity, a theory that suggests space isn't continuous, like a sheet, but pixelated, built from finite building blocks, like a cosmic quilt. Each thread, a loop of area, each junction, a node of volume. Unlike theories chasing new particles or extra dimensions, loop quantum gravity asks the most elemental question: what is space, and can it be broken down? This suggests that the universe is not a smooth flow, but a finely grained lattice, where each element of space is a standalone entity with its own behavior, forming a silent architecture that underlies every movement of the cosmos. By zooming into the very essence of what we think of as emptiness, loop quantum gravity offers a revelation that space may be as composed and structured as matter, and that beneath the curves we call geometry lies a system of logical threads holding it all together. At its core, loop quantum gravity proposes that just as matter is quantized into atoms and energy into photons, space itself is composed of fundamental quanta, minimum units of area and volume that can't be further divided. These aren't metaphors, they're measurable predictions. If true, the smooth curves of Einstein's spacetime are illusions, emergent properties of a much more granular foundation. This suggests that the universe is not a smooth flow, but a finely grained lattice, where each element of space is a standalone entity with its own behavior, forming a silent architecture that underlies every movement of the cosmos. By zooming into the very essence of what we think of as emptiness, loop quantum gravity offers a revelation: that space may be as composed and structured as matter, and that beneath the curves we call geometry lies a system of logical threads holding it all together. The motivation isn't poetic, it's a deep rift in physics. General relativity treats gravity as the bending of space-time, smooth and continuous. Quantum mechanics insists nothing is continuous. Everything fluctuates. Everything is quantized. When we try to unify them, like inside a black hole or at the Big Bang, the math breaks. Loop quantum gravity addresses this by treating space itself as quantum, composed of interwoven loops that define geometry from the ground up. This suggests that the universe is not a smooth flow, but a finely grained lattice, where each element of space is a standalone entity with its own behavior, forming a silent architecture that underlies every movement of the cosmos. By zooming into the very essence of what we think of as emptiness, loop quantum gravity offers a revelation that space may be as composed and structured as matter, and that beneath the curves we call geometry lies a system of logical threads holding it all together. In this framework, space isn't a passive backdrop, it's dynamic, with its own quantum state. Geometry arises through connections in a network of loops, described mathematically as spin networks, webs where edges carry quantum values of area and nodes represent volume. These evolve into four-dimensional spin foams, the scaffolding of space over time. In this picture, moving through space means hopping from loop to loop, not traveling a smooth path, but stepping across the quantum stones that make up the universe. These loops aren't embedded in space, they are space. This suggests that the universe is not a smooth flow, but a finely grained lattice, where each element of space is a standalone entity with its own behavior, forming a silent architecture that underlies every movement of the cosmos. By zooming into the very essence of what we think of as emptiness, loop quantum gravity offers a revelation that space may be as composed and structured as matter, and that beneath the curves we call geometry lies a system of logical threads holding it all together. What makes loop quantum gravity powerful is its simplicity. It doesn't rely on hidden particles or extra dimensions. It builds from general relativity and quantum theory, and it leads to stunning implications. For instance, it introduces a smallest possible area and volume. Below these, space ceases to have meaning. In classical physics, black holes end in singularities of infinite density. Loop quantum gravity suggests that collapse stops at the smallest volume, avoiding singularities altogether. This leads to the proposal of black hole bounces, where matter compresses, then re-expands, potentially birthing a new universe. This model can also reframe the Big Bang, not as a beginning, but a bounce from a previous contraction. This suggests that the universe is not a smooth flow, but a finely grained lattice, where each element of space is a standalone entity with its own behavior, forming a silent architecture that underlies every movement of the cosmos. By zooming into the very essence of what we think of as emptiness, loop quantum gravity offers a revelation that space may be as composed and structured as matter, and that beneath the curves we call geometry lies a system of logical threads holding it all together. Loop quantum gravity offers insights into space's microscopic structure. If areas and volumes are quantized, then even black hole surfaces are made of tiles, each tile a unit of area. This aligns with Stephen Hawking and Jacob Bekenstein's findings that black hole entropy relates to surface area. Loop quantum gravity explains this entropy as the number of ways loops can weave a horizon. Each spin network configuration counts. Thus, loop quantum gravity doesn't just theorize. It predicts physical properties like entropy and energy, building a quantum cosmology where the universe is a dynamic network of geometry, not particles in space, but space as geometry. This suggests that the universe is not a smooth flow, but a finely grained lattice, where each element of space is a standalone entity with its own behavior, forming a silent architecture that underlies every movement of the cosmos. By zooming into the very essence of what we think of as emptiness, loop quantum gravity offers a revelation that space may be as composed and structured as matter, and that beneath the curves we call geometry lies a system of logical threads holding it all together. Even time is reshaped. In general relativity, time bends with space. In loop quantum gravity, it emerges from changing networks. Time isn't a background. It's the unfolding of quantum connections. When loops form, interact, vanish, those are the ticks of the universal clock. Time becomes relational, not absolute. At the smaller scales, time may stall, flicker, or even disappear. There may be no before. Only network states changing without a master timeline. This suggests that the universe is not a smooth flow, but a finely grained lattice, where each element of space is a standalone entity with its own behavior, forming a silent architecture that underlies every movement of the cosmos. By zooming into the very essence of what we think of as emptiness, loop quantum gravity offers a revelation that space may be as composed and structured as matter, and that beneath the curves we call geometry lies a system of logical threads holding it all together. The beauty of loop quantum gravity lies not just in its math, but in how it re-enchants reality. The void is no longer void, it's a web of connections. Every breath, every movement is a ripple in the quantum mesh. You are not separate from it. You are a local knot in the cosmic weave, not passing through space, but composed of it. This suggests that the universe is not a smooth flow, but a finely grained lattice, where each element of space is a standalone entity with its own behavior, forming a silent architecture that underlies every movement of the cosmos. By zooming into the very essence of what we think of as emptiness, loop quantum gravity offers a revelation that space may be as composed and structured as matter, and that beneath the curves we call geometry lies a system of logical threads holding it all together. So next time you look at the stars, imagine the space between them as textured, pixelated, alive. Picture a vast lattice, not of matter, but of loops, building space itself, defining reality's shape. Loop quantum gravity doesn't just ask what space is, it dares us to see it as something woven, quantized, and alive beneath the illusion of smoothness. A quiet rhythm of loops spinning the universe into being. This suggests that the universe is not a smooth flow but a finely grained lattice, where each element of space is a standalone entity with its own behavior, forming a silent architecture that underlies every movement of the cosmos. By zooming into the very essence of what we think of as emptiness, loop quantum gravity offers a revelation. That space may be as composed and structured as matter, and that beneath the curves we call geometry lies a system of logical threads holding it all together. Geons, particles made purely from gravity. What if matter could be made not from atoms, not from quarks, not from any substance at all, but from gravity itself, bent and folded into a knot so intricate that it holds its own shape, persists in time, and behaves like a particle? Imagine a world where the very thing we think of as a force, gravity, is not just shaping matter but becoming it, curling back upon itself in closed loops and eddies of space-time that mimic mass, momentum, and identity. This is the wild yet rigorously formulated idea behind geons, short for gravitational electromagnetic entities, first proposed by physicist John Archibald Wheeler. In essence, a geon is a localized bundle of energy, specifically gravitational or electromagnetic waves, that's trapped by its own gravitational pull. There is no underlying mass, no core, no hidden particle. The energy itself, through the fabric of curved space-time, creates a self-contained structure that acts like a particle, even though it's made entirely from fields. It's a whirlpool with no water, a tornado with no air, just pure geometry folded in on itself so tightly that it becomes a thing. And in this radical vision, the boundary between force and matter begins to dissolve. If gravity can produce structures that persist and interact like particles, then maybe our assumptions about what matter is have always been incomplete. Perhaps we've been trying to build the universe out of Lego bricks, not realizing that the very table beneath them could be molded into those shapes all along. To grasp why geons matter, we need to rethink what a particle is. In quantum field theory, particles are excitations in fields, ripples of specific energy that behave predictably. Electrons, photons, neutrinos, each has mass, charge, spin. But all of them are built on top of space-time, using it as a static background. Geons, however, don't ride on the fabric of the universe. They are the fabric, twisted into coherence. Picture space-time as an endless sheet. Now imagine a pulse of energy, say, gravitational waves, moving across it. Usually such waves spread out, dissipate, lose their shape. But under the right conditions, the curvature caused by the energy can fold back around, creating a kind of gravitational trap. The energy becomes caught in a loop, a self-sustaining knot of space-time that doesn't require matter to hold it together. That's a geon. And here's the breathtaking part. This configuration can mimic many of the features of particles. It can be localized in space, it can move, it can carry angular momentum, it can interact. But it is not a particle in the traditional sense. It is a pattern, a self-bound structure made entirely from the interaction of energy and curvature. The geon doesn't have an inside, no smaller bits to break into. It is what it does, held together by its own gravitational dance. Wheeler's proposal came at a time when physicists were struggling to unify the forces of nature, to find a theory that could describe both gravity and quantum phenomena. Geons offered a tantalizing bridge. If matter could arise purely from geometry, then maybe the distinction between matter and space-time is artificial. Maybe all the universe's complexity, atoms, molecules, life, could be built from self-sustaining patterns in the curvature of space. And yet, geons also pose deep challenges. In classical general relativity, they are unstable. Over time, they radiate energy and disperse. But in the quantum version of gravity, still being developed, they might gain new life. Quantum corrections could stabilize them. Quantum fluctuations might lock them into place. Some researchers have even speculated that geons could be a step toward understanding the true nature of particles. not as objects, but as topological features in a dynamic, self-interacting universe. Think of a knot in a rope. You can't remove it without moving the rope itself. A geon is similar. It's not a thing placed in space, but a twist of space itself, like a persistent echo shaped into permanence. Geons challenge not just physics, but metaphysics. They ask, can something exist without substance? Can structure alone be enough to make something real? In traditional thinking, objects need material. They must be made of something, but Geons suggest that identity can arise from behavior, from patterns of energy that hold form through internal balance. This isn't a new idea entirely. Fields like fluid dynamics and condensed matter physics show that emergent behaviors can seem particle-like. Vortices in superfluids, for instance, can behave as if they are particles, even though they're just organized motions in a continuous medium. Geons take this to the cosmic scale. They're vortices in the fabric of space-time itself. They suggest a universe where being is not about stuff, but about stability, about balance and resonance and coherence within the rules of the system. If a structure can persist, if it can carry energy, if it can interact, then maybe that's enough. Maybe matter is just the universe playing a song so tightly wound that it hums in one place and not another. This leads to even deeper possibilities. Could all particles be geons in disguise? Could electrons, quarks, even photons be nothing more than stabilized loops or knots in some higher order gravitational or quantum field? Could charge, mass, and spin be emergent properties from different ways of knotting spacetime? These are not idle dreams. They're research questions. Modern extensions of general relativity, like loop quantum gravity, or various topological field theories, explore these ideas with growing precision. In some models, particles are seen as braids, in quantum spacetime, twists that stay intact due to topological constraints. In others, the very fabric of space behaves like a fluid, and particles are localized excitations, like bubbles or waves, that emerge from the fluid's properties. Geons, in this broader context, are no longer exotic. They are part of a growing recognition that nature may be more about relations than ingredients, more about patterns than pieces. And if we continue down this path, we might discover that the hardest, most material parts of our world, the chair you sit on, the atoms in your hand, are not made of building blocks at all, but of bound energy, wrapped and looped into self-sustaining harmony. The elegance of geons lies not just in their novelty, but in how they unify seemingly opposing concepts. They are particle and wave, matter and geometry, local and global. They demonstrate that energy can be self-aware in a sense, not conscious, but self-stabilizing. And they hint at a universe where dualities are illusions, where force and form are not separate categories, but two sides of the same curvature. The implications stretch outward in every direction. Cosmologically, geons might provide seeds for galaxy formation, or hints about early universe structure. Quantum mechanically, they might offer pathways to understanding confinement, why some particles, like quarks, can never be isolated. Even philosophically, geons invite us to reconsider what it means to be. If all things are temporary patterns in a shifting sea of space-time, then permanence is not the foundation of reality, process is. And that makes every interaction, every motion, every fluctuation a kind of creation. You don't need matter to make the world, you just need the right conditions for space to bend back on itself, to hold its own shape, to become a self-sustaining twist in the flow. So next time you think of gravity as just a force that pulls you down or curves planets into orbits, try imagining it differently. See it not just as a warping of paths, but as a sculptor of existence. Picture a place in the universe where gravity has folded so tightly, so symmetrically, that it creates a pocket of coherence, a geon humming silently, drifting like a particle, never asking for substance, only shape. In that picture, the line between nothing and something begins to blur. And maybe that's the deepest truth of all, that existence isn't built from stuff, but from stability within the rules, that particles are not dots in space, but dances of space, and that the cosmos, in all its complexity, may be nothing more and nothing less than geometry, learning to sing, axions, and other exotic particles born from broken symmetries. What if the universe whispered secrets, not in the brightness of stars or the explosion of galaxies, but in the quiet asymmetries hidden deep within its equations? Small, subtle breaks in balance that gave rise to particles no one has yet seen, but which might shape everything from the core of matter to the fate of the cosmos. Among these whispered possibilities lies a particularly elusive and graceful idea, the axion, born from the attempt to solve a nagging inconsistency in particle physics. The axion is not just another hypothetical particle, it's a consequence of a broken symmetry. A ghost-like solution to a problem most people never knew existed, yet one that might explain the invisible glue that holds the universe together. Unlike electrons or photons, which are familiar parts of everyday physics, axions come from the hidden machinery of theoretical elegance, from a symmetry known as the Peck-Fay-Quinn symmetry, that was invented not to describe nature, but to protect it from contradiction. You see, quantum chromodynamics, the theory that describes the strong nuclear force, has a flaw. It allows for a type of behavior that would violate CP symmetry, the combined symmetry of charge and parity. But nature refuses to play along. Experiments show that quantum chromodynamics behaves as if CP is preserved. Why? That's where the axion enters. Not as an afterthought, but as a required artifact of restoring harmony to a broken framework. It emerges naturally from the mathematics as a stabilizing field, its particle a tiny, neutral, nearly undetectable entity that might permeate the universe like mist, silent and almost weightless, yet cosmically significant. To understand why axions are more than just mathematical decorations, you have to look deeper into the world of symmetry, one of the most powerful guiding principles in physics. Symmetry is not just aesthetic, it's predictive. Every conservation law, from energy to momentum to electric charge, corresponds to a symmetry in the laws of physics. But when these symmetries break, remarkable things happen. In the early universe, when temperatures were unimaginably high, symmetries between forces and particles reigned. But as the universe expanded and cooled, these symmetries fractured, like ice crystallizing from water. And from those fractures new particles were born. This is the core idea behind spontaneous symmetry breaking. It's how the Higgs boson came to be, how W and Z bosons gained mass, how forces that once were unified grew apart. And in the case of the strong CP problem in quantum chromodynamics, the proposed symmetry that could fix it, Peck-Fay-Quinn symmetry, must also break. That break births the axion. This particle doesn't just patch the theory, it could also explain one of the greatest mysteries in modern cosmology, dark matter. Because axions, with their ultra-low mass and neutral charge, are perfect candidates for the invisible scaffolding that holds galaxies together. What makes axions even more fascinating is their paradoxical nature. They are both incredibly weak and potentially incredibly abundant. If they exist, they would interact so feebly with ordinary matter that trillions could pass through you every second without leaving a trace. But that very weakness is what makes them stable over cosmic time, ideal for dark matter. Unlike WIMPs, weakly interacting massive particles, which have so far evaded every detector, axions offer a different profile. They're not just elusive because of their size or speed, but because they are fundamentally tied to the structure of vacuum itself. They could form a kind of background field across the universe, oscillating gently like a low-frequency hum beneath all of reality. In some theories, axions are not just passive dark matter, but active participants in cosmic evolution, affecting how stars cool, how galaxies rotate, even how black holes evolve. And if we could detect them, by their subtle effect on electromagnetic fields in clever lab setups, or by anomalies in stellar behavior, We wouldn't just be adding another particle to the zoo. We'd be confirming that the universe still respects the deep principles of symmetry, even when it chooses to break them. But axions are just the beginning. Broken symmetries give rise to an entire family of exotic particles that may lurk in the shadows of physics. Majorons, named after Etera Majorana, are hypothetical particles associated with neutrino masses, potentially arising from the breaking of lepton number symmetry. Familons could come from broken family symmetries, explaining why different generations of quarks and leptons exist with such strange mass hierarchies. Dilatons might be linked to scale symmetry, offering insight into the structure of spacetime itself. Even hypothetical gauge bosons like the dark photon are thought to originate from broken symmetries in a hidden sector, an entire mirror world of particles and forces that don't interact with ours except through subtle portals. These are not just theoretical amusements. They arise naturally from the effort to make our models consistent, to fill in gaps, to explain why certain processes happen and others do not. Each of these particles is a clue, a whisper from the deeper architecture of the universe, hinting that the reality we experience is only a sliver of what truly exists. What unites all of these exotic particles is the concept of symmetry breaking as a creative force. In everyday language, breaking something usually means destruction. But in physics, breaking a symmetry creates diversity, structure, and new behavior. It's how the featureless early universe developed complexity. It's how the same force can split into the electromagnetic and weak forces. It's how mass arises, how particles distinguish themselves, how fields form textures and patterns. Broken symmetries are like cracks in a frozen lake. Each one reveals a hidden layer beneath, and each fracture leads to a new form, a new rule, a new player in the game of nature. Axions, majorons, dilatons. Each is a fossil of a broken rule, a signpost that tells us where nature once changed its mind. And following these signposts doesn't just help us discover new particles. It teaches us how to read the universe like a poem, whose verses are written in fields, and whose rhythm is governed by the breaking of balance. Efforts to detect axions and other symmetry born particles are among the most creative in modern science. Physicists are designing resonant cavities, ultra-sensitive magnetic detectors, and even using astrophysical observations to capture the quiet signal of axions, turning into photons in magnetic fields. Projects like ADMX, CAST, and MADMAX are hunting for this conversion effect, hoping to catch a flicker of evidence. Meanwhile, theoretical physicists are exploring how axions might affect black holes. If ultralight axions exist, they could cause spinning black holes to shed their angular momentum in a process called superradiance, leaving behind observable fingerprints in gravitational waves. Others study how axions could affect neutron stars, supernovae, or even the cosmic microwave background. It's a multidisciplinary treasure hunt, where clues might lie in particle accelerators, in deep space, or in the quiet hum of a magnetic coil cooled near absolute zero. And the stakes are enormous, not just for axions themselves, but for what they represent, a validation that the universe cares about. Internal consistency, that symmetry and its fractures aren't just accidents, but the engine of everything. So what does this mean for us? For the way we see the cosmos? It suggests that the universe is not static, but a result of decisions, spontaneous, necessary decisions made at the deepest levels of physics, where symmetries existed, then broke. And from their breaking emerged the diversity of particles, forces, and phenomena we now observe. It means that nothing we take for granted, mass, spin, charge, even the vacuum, was inevitable. Each is a consequence of a deeper rule bending, of a balance tipping slightly, and producing a cascade of structure. And within that cascade are hidden players, exotic, silent, but perhaps omnipresent, whose properties we are only now beginning to imagine. To chase them is to chase the roots of the universe's decisions, to understand not just what the universe is, but why it chose to be this way and not another. So the next time you hear about particles with names you've never encountered, axions, majorons, familons, dilatons, don't dismiss them as distant abstractions. See them instead as evidence of a cosmic story far richer than our senses can tell. Imagine a universe sculpted by broken symmetries, where even the tiniest imbalance gives birth to new laws, new entities, and new possibilities. And consider the quiet, elegant possibility that the matter that makes up you, me, and everything around us may not be the only story worth telling. That, somewhere, just beyond our current reach, the universe is still singing in frequencies we've yet to hear, vibrating with particles that don't want to be seen, but long to be understood. Cosmic censorship hypothesis. What physics won't let you see? What if the universe had secrets so dangerous, so disruptive to the very structure of reality, that it built walls around them? Cosmic barriers beyond which no information can escape. Events so extreme that nature itself refuses to let you observe them. Imagine a realm where the laws of physics are pushed to their breaking point, where gravity becomes infinite, time distorts into meaninglessness, and the very idea of space dissolves into a paradox. But just as you approach this forbidden edge, the universe veils it, cloaks it, hides it behind a perfect curtain of silence. This is the eerie, powerful idea behind the cosmic censorship hypothesis, a proposal that says the universe protects its own sanity by concealing its most violent truths. At its heart lies a simple but profound question. If general relativity predicts the formation of singularities, places where space-time curvature becomes infinite and the laws of physics collapse, why don't we see them? Why do we always find them safely tucked away inside black holes, hidden by event horizons? The hypothesis, introduced by Roger Penrose in 1969, suggests an answer that feels almost moral in tone. The universe censors its own chaos, ensuring that singularities, those naked anomalies where predictability dies, never reveal themselves directly to outside observers. If true, it would mean that no matter how strange or destructive a region of space-time becomes, the damage will always be sealed off, ensuring the rest of reality continues undisturbed, uncorrupted by the wild core hidden within. To understand why this idea even exists, we must first step back and face the unflinching predictions of Einstein's general theory of relativity, which allows, even demands, the existence of singularities. These are not just weird spots in space, they are breakdowns in the fabric of reality itself, where time ceases to be time and space folds infinitely inward. The most famous example is the singularity at the center of a black hole, a point of infinite density and zero volume, where gravity becomes so intense that nothing, not even light, can escape. But not all singularities are equal. Some are neatly wrapped in event horizons, sealed behind boundaries that mark the point of no return. These are the singularities that respect cosmic censorship, but others, naked singularities, are not hidden. They are exposed, raw, and visible in theory to the rest of the universe, threatening the very predictability that physics relies on. A naked singularity would be a place where determinism breaks down, not just locally, but globally. If you could see a naked singularity, you could observe effects with no knowable cause, outcomes without rules, and perhaps even violate causality itself. That's why Penrose proposed that such entities simply cannot form, or at least, if they do, they can never be observed. The universe would censor them, always covering them up with an event horizon or some other mechanism to prevent their influence from leaking into the rest of space-time. But is this censorship built into the laws of physics, or just a comforting idea to preserve our understanding of the cosmos? The truth is, no one knows for sure. The cosmic censorship hypothesis remains unproven, neither confirmed nor falsified. It comes in two flavors: the weak version, which says that singularities cannot be observed from the outside and must be hidden behind horizons, and the strong version, which claims that the laws of physics remain deterministic everywhere, even at the edge of singularities. Weak cosmic censorship is what protects us from seeing the breakdown of physics. Strong cosmic censorship would ensure that physics never breaks down in the first place, at least in a way that matters. These ideas are not just theoretical. They influence everything from how we model collapsing stars to how we think about the birth of the universe. In simulations of gravitational collapse, certain configurations seem to hint at the possibility of naked singularities forming, yet under slightly different conditions. An event horizon forms just in time, covering the singularity. It's as if space-time itself conspires to protect its secrets. But these are delicate, finely tuned cases, and no consensus exists. Some physicists argue that under realistic physical conditions, cosmic censorship always holds. Others believe it may be violated in rare, exotic scenarios, especially in higher dimensional spacetimes or in modified theories of gravity. The deeper mystery is not just whether singularities are hidden, but what they mean. If a singularity is truly naked and observable, what would it even look like? Since the laws of physics fail at the singularity, any prediction becomes impossible. Light paths diverge, information flows in undefined ways, and the equations that describe time and space give no guidance. Such a region would not just defy understanding, it would defy explanation. Observing one might allow time travel, unpredictable energy bursts, or violations of conservation laws. That's why their mere existence threatens the core of scientific predictability. In a universe with visible singularities, cause and effect might unravel. You could watch an object appear from nowhere, a light beam trace a loop in time, or a region of space where every known law gives contradictory answers. That's why many physicists, while intrigued by the possibility, hope that cosmic censorship is true. It acts as a firewall, preserving the causal structure of the universe by keeping the unknowable hidden from view. And yet, nature rarely cares about our preferences. The history of science is filled with principles, once thought sacred: Euclidean geometry, absolute time, fixed space, that were eventually overturned. Perhaps cosmic censorship, too, is an illusion we cling to out of necessity, a temporary placeholder for a truth we are not yet ready to see. Quantum gravity might offer new insights into this mystery. In classical general relativity, singularities are unavoidable under certain conditions, as shown in the singularity theorems of Penrose and Hawking. But those theorems don't account for quantum effects. If space and time are quantized at the smallest scales, perhaps singularities don't truly exist. Perhaps they are replaced by something more complex, more manageable, more understandable. In loop quantum gravity, for example, the fabric of space is made of discrete loops, and the equations suggest that gravitational collapse might halt or rebound before forming a true singularity. In string theory, singularities are often smoothed out by higher dimensional dynamics or Brane interactions. If these models are correct, cosmic censorship might not be needed, because the breakdown of physics never actually occurs. But until we have a full theory of quantum gravity, we are left with approximations, incomplete pictures, and a philosophical question: does nature hide its flaws out of necessity? Or are we just too limited to understand what lies beyond the veil, beyond the mathematics and models? Cosmic censorship touches something primal in us, a fear of the unknowable, of regions where logic dies and meaning evaporates. In many ways, it resembles ancient myths of forbidden knowledge, of gods who hide dangerous truths from mortals. Except here, the gods are the laws of nature themselves, and the forbidden fruit is the singularity, lying at the heart of a black hole or the core of a collapsing star. If we could see such a region, if cosmic censorship failed, what would it teach us? Would it free us from the limitations of current physics, or drown us in chaos we can't contain? Would it open new doors, or shatter the frame entirely? Perhaps the real danger isn't in what we might see, but in what it would mean for everything else. Predictability, causality, determinism. These aren't just scientific terms, They are the backbone of rational thought, of science itself. A universe that allows naked singularities might still function, but it wouldn't be understandable. It would be a place where not everything can be known, not even in principle. A cosmos with permanent blind spots, and no way to look beyond them. So the next time you think about black holes, try not to imagine them just as traps or exotic curiosities. Picture them as locked vaults of forbidden truth, sealed not by chance, but perhaps by the universe's own hand. Maybe physics, in its deepest form, is not just about describing what can happen, but about guarding against what must not. Maybe singularities are not just endpoints of gravity, but edge. Cases in reality, so sharp, so fragile, that seeing them would collapse the rules we live by. Whether the cosmic censorship hypothesis stands or falls, it forces us to confront a possibility more profound than any equation, that the universe may not be infinite in what it allows us to witness, and that what lies beyond the veil is not just unknown, but unknowable by design. Asymptotic safety. Can gravity be renormalized like other forces? What if the force we understand the least, the very one that anchors us to the ground, governs the motion of planets, and shapes the expansion of the cosmos, could finally be tamed not with exotic dimensions or unseen particles, but through a quiet, elegant idea hiding in plain sight, that gravity, despite all odds, might become well behaved at the highest energies, if we look at it the right way. This is the tantalizing promise of asymptotic safety, a concept born from the effort to reconcile Einstein's theory of general relativity with the strange, precise world of quantum mechanics, not by changing gravity's nature, but by exploring how it flows, mathematically speaking, across scales. At first glance, gravity refuses to be quantized like other forces. Attempts to treat it with the same tools we use for electromagnetism, or the strong and weak nuclear forces, lead to infinities that spiral out of control, breaking predictions, and threatening the very foundation of a quantum theory of gravity. But what if those infinities aren't a problem to be avoided, but a path to something deeper? In the asymptotic safety approach, the idea is simple, yet profound. Instead of assuming that gravity behaves chaotically at high energies, we explore the possibility that it settles into a safe zone, a high-energy fixed point, where all its wild quantum fluctuations stabilize. In other words, gravity might renormalize, not in the traditional sense of becoming milder at high energies like QGD or QCD, but by locking into a predictable structure where only a finite number of parameters govern its behavior, even at the Planck scale where other theories break. To understand why this idea is so powerful, we need to dive briefly into what makes quantum field theories tick. When physicists quantize a force, they don't just describe it, they explore how its behavior changes with energy, using a mathematical technique called the renormalization group. This is like zooming in and out on a painting to see how the picture changes at different scales. Some theories, like electromagnetism, are well-behaved. Their predictions remain consistent and accurate at both low and high energies, because the infinities that arise can be absorbed into a few constants. These theories are called renormalizable. Others, like general relativity, seem to resist this process. When you quantize gravity in the standard way, the equations explode with an infinite number of new terms, each requiring its own constant to tame. This makes predictions impossible, unless, somehow, all those wild terms flow into a fixed structure as you move to higher and higher energies. That's where asymptotic safety comes in. It proposes that despite its unruly appearance, gravity might become safe, predictable, and constrained at high energy scales, not by simplifying, but by finding a hidden order in the chaos. The term asymptotic safety was coined by theoretical physicist Steven Weinberg in 1976, who imagined that gravity might possess a non-trivial ultraviolet UV fixed point, a point in the renormalization group flow, where the theory becomes scale invariant, meaning its structure remains unchanged no matter how high you crank the energy. This is different from asymptotic freedom, seen in the strong nuclear force, where the force weakens at higher energies. In asymptotic safety, the strength of interactions might not vanish, but the form of the theory stops changing. Think of it like a raging river that eventually hits a plateau and flows smoothly from there, chaotic motion settling into stable structure. If gravity behaves this way, it could mean that a quantum theory of gravity is not only possible but self-contained, requiring no additional physics, no new particles, no string theory, no extra dimensions, just Einstein's general relativity, extended to account for quantum fluctuations, and a stable high-energy behavior encoded in the flow of its couplings. This would be a monumental shift. Not just a way to patch gravity, but a full-blown, predictive, non-perturbative framework that could explain black holes, the early universe. The challenge lies in the complexity of the equations. Unlike simpler quantum field theories, the equations for gravity, especially in the non-perturbative regime, are too tangled to solve directly. But physicists have developed powerful tools to explore them numerically and analytically. One approach is known as the functional renormalization group, a method that lets you track how the effective action, essentially the rulebook of a quantum field, changes with scale. Using the functional renormalization group techniques, researchers have found evidence that a non-trivial UV fixed point does exist in several simplified models of quantum gravity. These findings are not definitive, but they're consistent, robust across methods, and suggestive of a deep truth waiting to be uncovered. Intriguingly, these results often imply that only a few parameters, maybe 2 or 3, are needed to describe gravity at all scales. That's important. It means the theory is predictive. You don't need infinite inputs to get finite answers. The wildness of quantum gravity becomes manageable because its behavior flows towards safety, and the implications don't stop with pure gravity. When you incorporate matter fields like those in the standard model into the picture, the structure of the theory becomes even richer. Some versions of asymptotic safety suggest that gravity might constrain the possible behaviors of matter at high energies. In this view, the coupling constants of particle physics, like the strength of the Higgs field or the mass of the top quark, aren't arbitrary. They are pulled toward specific values by the gravitational fixed point, like stones falling into a well. This could explain why the standard model's parameters are so finely tuned, and why the Higgs boson has the mass it does. Even the cosmological constant, one of the deepest puzzles in physics, might be shaped by the flow of gravitational interactions. If gravity is asymptotically safe, then the early universe's evolution, inflation, and even dark energy could be influenced by the same high-energy behavior. Suddenly, the theory doesn't just rescue gravity, it connects it to everything. Despite its potential, asymptotic safety is still a frontier, with many open questions. Is the UV fixed point truly unique? Do different versions of the theory all converge to the same behavior? Can it be embedded in a broader framework that includes quantum thermodynamics or quantum information? Can it explain entropy, causality, and the arrow of time? And perhaps most importantly, is it testable? The hope is that gravitational waves, black hole mergers, or precise cosmological measurements might carry imprints of quantum gravity. Some models predict deviations from general relativity at extreme energies, subtle fingerprints that advanced detectors could spot. Others look for consistency with known low-energy behaviors, ensuring that the theory remains grounded in observation. There is no single test for asymptotic safety, but a network of clues, mathematical, numerical, experimental, that slowly build a case, one calculation at a time. More broadly, the philosophy behind asymptotic safety invites a different way of thinking about nature. It says that the universe may not need to be rewritten with every new discovery. Instead, it might be deeply self-regulating, with even its wildest forces, like gravity, finding equilibrium at the highest energies. It's an economy of structure, a balance between complexity and constraint where the most unpredictable things are actually guided by invisible order. Asymptotic safety keeps its feet on the ground, or at least on the spacetime fabric, using tools we already trust. It doesn't ask for new particles, new dimensions, or speculative landscapes. It simply asks, what if the chaos of gravity contains its own resolution? So the next time you feel the weight of gravity pulling you toward the Earth, try to imagine that pull not as a brute force, but as a whisper from the edges of the quantum world. A force that, despite its resistance to being tamed, may ultimately be part of a grand, self-consistent design. Picture a universe where even the most unruly laws have limits, where infinities don't destroy meaning, but guide us to deeper truths. In that view, gravity is not a failure of quantum theory. It is its final test, and asymptotic safety may be the path through which that test becomes a triumph. Quantum thermodynamics and the origin of space. What if the very fabric of space wasn't a passive stage on which matter performs, but a thermodynamic result, a consequence of heat, information, and quantum probability stitched together, not by geometry, but by entropy? Imagine for a moment that space is not a given but an emergent phenomenon, something that crystallizes from microscopic quantum processes. The way pressure emerges from atoms bouncing inside a balloon, or the way temperature emerges from the average behavior of trillions of molecules. Now ask yourself, what if everything you perceive as distance, direction, or dimension arises from a deeper principle of energy exchange, where space itself is not a backdrop for physics, but a thermodynamic illusion born from the same rules that govern heat flow and information loss? This is the provocative territory explored by quantum thermodynamics and the origin of space, a growing frontier where gravity, quantum mechanics, and statistical mechanics begin to melt into one another, suggesting that space-time is not fundamental but derivative, an effect, not a cause, sculpted from entropy gradients and the probabilistic flow of quantum information. In this view, the curvature of space is not simply a geometric property, it's a thermal response, an echo of underlying quantum states rearranging themselves to maximize disorder. You're not moving through space. You're watching space emerge from the thermodynamic bookkeeping of the universe. To understand how such a radical view could hold weight, we need to look at the surprisingly deep connections between gravity and thermodynamics. Connections that have been appearing like whispers across decades of physics. The story began in the 1970s, when physicists studying black holes, those dense gravitational maelstroms, where even light cannot escape, discovered something deeply strange. According to general relativity, black holes should be perfectly cold and dead, absorbing everything, emitting nothing. But then came Jacob Bekenstein, who argued that black holes should have entropy, a measure of disorder, proportional not to their volume, but to the area of their event horizon. Then Stephen Hawking shocked the world by showing that black holes must also have a temperature, and that they emit radiation due to quantum effects near the event horizon. This so-called Hawking radiation implied that black holes aren't entirely black. They slowly evaporate, radiating away their mass. This wasn't just a curious feature, it was a crack in the wall separating gravity from thermodynamics. It suggested that horizons, the edges of what can be known or observed, might always be tied to heat, entropy, and the deep mechanics of information. And that raised an unsettling question. If black holes are thermodynamic systems, then is gravity itself a thermal effect? Could the very equations of Einstein's general relativity be just a large-scale approximation of something statistical? That idea, bold as it sounds, was taken seriously by physicists like Ted Jacobson in the 1990s, who made a startling proposal, starting with nothing but the laws of thermodynamics: energy conservation, entropy, and temperature gradients. You can derive the Einstein field equations. That's right. You don't need to assume gravity. You can build it from heat. This flips the entire hierarchy of physics. Instead of treating thermodynamics as an emergent property of gravity, gravity becomes an emergent property of thermodynamics. In Jacobson's framework, Space-time curvature rises from the tendency of local quantum systems to maximize entropy. Where there is a gradient in information flow, there is curvature. Where there is a boundary in what can be known, it pointed toward a profound principle: that space-time geometry may be the macroscopic limit of microscopic quantum degrees of freedom, just like gas pressure is the macroscopic limit of molecules in motion. This interpretation turns the vacuum into a thermodynamic sea, where space itself is a derivative concept, useful, measurable, but not fundamental. Fast forward to more recent developments, and we find even stronger support for this view in the strange world of quantum thermodynamics. The study of how thermodynamic laws apply when energy, entropy, and information are governed by quantum rules. In classical thermodynamics, you deal with averages, large numbers of particles, smooth gradients, reliable outcomes, but quantum systems are finicky. They can exist in superpositions, become entangled, and fluctuate wildly in behavior. Yet remarkably, thermodynamic principles still hold. Entropy increases, heat flows from hot to cold, work can be extracted, but with deep nuances. In this regime, energy and information are two sides of the same coin. And here's where things get stranger. In some frameworks, the structure of space itself can be inferred from the entanglement structure of quantum states. This is the idea behind emergent space from entanglement, supported by research in areas like ADS over CFT correspondence and tensor networks. If you map how quantum systems are entangled with one another, how information is shared and hidden, you can reconstruct the shape of space. That means geometry isn't input, it's output. It's the shadow of information flow. One of the most compelling illustrations of this comes from the work of Van Ramsdonk and others, who showed that when two quantum systems are entangled, the geometry between them becomes connected. Like stitching two regions of space-time together, break that entanglement, and the geometry splits. In this view, space-time is like a quilt sewn from entangled threads. The more you entangle, the closer things appear. The less you entangle, the farther apart they seem. Entropy, then, is not just a feature of thermal systems, it is the scaffolding on which space is built. This idea even appears in the holographic principle, which suggests that everything inside a volume of space can be encoded on its boundary. The number of bits required to describe a region scales, not with volume, but with surface area. Just like black hole entropy, and where there is information, there is heat. Where there is uncertainty, there is curvature. The shape of space could be nothing more than the shape of missing information, traced in thermal ink. So what does this mean for the origin of space itself? It means that in the earliest moments of the universe, before space expanded, before particles cooled, before anything had a shape, there may not have been a space at all. Only a roiling, fluctuating quantum system, dense with energy, rich with entanglement, and governed by thermodynamic flow. As this system evolved, patterns emerged. Some regions became more entangled than others. Information began to move in specific directions. Boundaries formed, and with those boundaries came the illusion of distance. Space wasn't there in the beginning. It arose from the way the universe chose to handle its own heat, its own randomness. And this gives a whole new flavor to questions we've asked for centuries. Where did space come from? What is its fabric made of? Why does it curve near mass? In this view, these aren't geometric puzzles. They are thermodynamic ones. The origin of space is the story of the universe, reaching thermal equilibrium, of entropy trying to maximize itself, and in doing so, giving rise to the dimensions through which we move. This perspective doesn't just offer philosophical comfort, it has potential predictive power. If space emerges from entanglement and thermodynamics, then deviations from expected geometry could reflect changes in information structure. Certain models predict that regions of space-time with low entanglement density might exhibit exotic properties, like reduced dimensionality, altered causal structure, or even violations of locality. Experiments at the frontier of quantum simulation, quantum gravity, and black hole thermodynamics are starting to probe these ideas. Could a sudden shift in a system's entanglement cause space itself to deform? Could gravity be manipulated not by mass, but by entropic gradients? Could future technologies create or dissolve space-time connections by engineering quantum states? These are no longer science fiction questions. They are emerging frontiers of inquiry. So the next time you feel the space around you, when you stretch your arm, walk across a room, or gaze up at the stars, try to imagine that space not as a given, but as a consequence, a shimmering thermodynamic mirage built from the quiet hum of quantum interactions and the hidden logic of entropy. What you call here and there may simply be coordinates on an entanglement map, drawn not by rulers, but by information flow, and in the grand heat exchange that is the universe, space might be nothing more than the shadow of that dance, the cooled shape of ancient quantum fire still glowing beneath our feet, the Swampland conjecture. Most universes shouldn't exist. What if the vast majority of universes we can imagine, even the ones that seem mathematically possible, even the ones that almost work, are not just unrealistic, but forbidden by the deepest rules of nature itself? What if the multiverse, that great ocean of theoretical worlds stretching out across the space of possibility, is mostly made of swamps, muddied regions of equations that look like they could describe a consistent universe, but upon closer inspection, simply fall apart? This unsettling idea lies at the heart of the Swampland conjecture, a bold and controversial proposal from theoretical physics that suggests that only a tiny island of all the possible solutions to string theory correspond to real, stable, and physically allowed universes, while the rest, an overwhelmingly vast rest, reside in a treacherous mathematical bog known as the Swampland. In this view, just because an equation appears to be internally consistent, or just because a field configuration seems like it could describe a viable cosmos, doesn't mean it actually can. The Swampland says, most of these theories are mirages, doomed from the start. Not because they're ugly or inelegant, but because they violate deep constraints we're only beginning to understand. It's a sobering thought that the laws of nature don't merely shape what is real, but rigorously exclude what could have been. And suddenly, the existence of this universe, our little bubble of stars, atoms, and minds, feels not just improbable, but miraculously permitted. To understand where this idea comes from, we need to go back to the vast mathematical landscape of string theory. Currently, our best hope for unifying all known forces, including gravity, into a single quantum framework. String theory doesn't just describe one universe, it describes a multiverse, a nearly infinite variety of possible configurations for space, time, matter, and energy, each determined by how the extra dimensions are curled, what fields are allowed to exist, and how strings vibrate within that background. These configurations are often referred to as the string landscape, a sprawling mathematical terrain of potential universes, each point on the landscape representing a consistent low-energy theory that might, in principle, describe a real world. For years, this landscape was seen as both an opportunity and a problem. An opportunity because it might contain a solution that matches our universe. A problem because there were just too many solutions, and no obvious way to choose among them. This made the theory flexible, but dangerously so. If everything is allowed, how can anything be predicted? That's where the Swampland conjecture storms in with a cautionary voice. Not all of these solutions are valid. In fact, most of them aren't. They live in the Swampland, where the mathematical ground is unstable, the fields are unphysical, and the quantum theory of gravity breaks down. The Swampland conjecture, as formulated by Qumran and others in the 2000s, aims to define sharp boundaries around which effective field theories can arise from a consistent theory of quantum gravity, such as string theory. In simpler terms, it tries to answer the question, if I give you a set of equations that describe a universe, how do you know whether they actually come from a deeper, stable theory that includes gravity? And the answer, according to the Swampland program, is that certain telltale features will disqualify most candidates. For instance, One core idea is the distance conjecture, which says that if you try to move too far in the space of possible field values, an infinite tower of particles suddenly becomes light, destroying the validity of your effective theory. Another is the de Sitter conjecture, which claims that stable universes with positive cosmological constant, like ours, which is accelerating, are either impossible or only metastable, meaning they are temporary and destined to decay. These constraints aren't arbitrary. They arise from the internal logic of string theory and the known features of black hole physics. But their implications are startling. They suggest that certain popular cosmological models, including many versions of inflation and dark energy, might not be derivable from a theory of quantum gravity at all. This strikes at the heart of modern cosmology. For decades, physicists have used effective field theory as a reliable tool to describe everything from particle interactions to the early universe. These theories work well within a certain energy range and don't try to explain gravity at the Planck scale. But the Swampland program argues that gravity leaves fingerprints even at low energies, and that if your theory doesn't match the rules of quantum gravity, it may be mathematically elegant but physically meaningless. In practice, this means that many beautiful models, built to explain how inflation might stretch space, or how dark energy might accelerate cosmic expansion, are in fact swampy. They don't have a UV completion, a deeper theory that remains consistent at all energy scales. In this light, the Swampland isn't just a metaphor, it's a warning. Don't build your theoretical house on unstable ground. Even if the equations look smooth, even if the predictions match observations, a subtle inconsistency in the gravitational behavior can doom the entire framework. And this makes our own universe feel less like a random accident and more like a narrow threading of a needle through a dangerous terrain. The philosophical consequences of this idea are profound. If most conceivable universes are in the Swampland, then the very fact that we exist in a universe with stable physics, stars, atoms, and complexity might be an enormous constraint. It's not just anthropic selection, it's gravitational selection. The universe had to obey not only the laws of nature as we observe them, but the deeper hidden rules of quantum gravity that disallow all but a razor-thin sliver of possible realities. That means that the constants we observe, the strengths of forces, the masses of particles, the properties of space, aren't just convenient or coincidental, they're allowed. That is, they lie on the habitable island in the sea of mathematical possibility. And everything else, countless other configurations that could have existed, that might have had stars and galaxies, even observers, are ruled out not because they're messy, but because they contradict the unseen laws that govern the marriage of gravity and quantum mechanics. Some critics argue that the Swampland conjectures are speculative, and they are right. This is frontier physics, where sharp answers are rare, and much is based on partial calculations and deep intuition. But others see in this program a way to bring predictive power back to string theory. Rather than accepting the landscape's vastness, the Swampland tells us what cannot happen. It draws a boundary, no matter how uncertain its edges. And within that boundary, physics must obey certain rules. For instance, the Swampland constraints can rule out certain inflationary models, disfavor static dark energy, and hint that our universe's accelerating expansion might be a transient illusion. They also predict that as fields roll across their potential, new particles will appear, light and numerous, collapsing, the low-energy approximation. This leads to testable implications for future experiments in cosmology and particle physics. It connects the ultra-small world of quantum strings with the ultra-large structure of space-time. Perhaps most intriguingly, the Swampland could offer insights into the nature of time and change itself. If our universe is not in a stable configuration, but rather balanced precariously in a metastable state, as the de Sitter conjecture implies, then it must decay, evolve, or transition into something else. Our cosmos may not be eternal. It may be a brief moment in a deeper cycle, or the crest of a thermodynamic wave destined to collapse. The Swampland forces us to accept the possibility that stability is the exception, not the rule. That the universe we live in is rare not because it's special, but because the laws that allow it are rare, and that changes how we think about existence. It reframes the question from, why is the universe the way it is, to how did it avoid being what it couldn't? So the next time you imagine a multiverse, a garden of branching realities where every possibility is played out, remember the Swampland. Not every path is walkable, not every universe can stand. Behind the elegance of equations lies a jungle of broken theories, tangled and forbidden. And somewhere in that maze, our universe found a path. Not because it had to, but because it could. That narrow path is not just a home, it's a miracle of permission, a universe that shouldn't exist, but does. Emergence of time, when the past is not a prerequisite. What if time, the very thing we assume to be ever, present and constantly flowing, isn't actually fundamental at all, but something that emerges under specific conditions, something that only appears when the universe becomes complex enough to need it? What if the ticking of clocks, the aging of stars, the rhythm of your heartbeat, and the memory of yesterday are not signs of time's existence, but clues to its construction, assembled from patterns, correlations, and thermodynamic gradients, rather than built into the core of the cosmos? The idea that time is emergent, that it's not a prerequisite for existence, but a consequence of it, is one of the most radical and intriguing notions in modern theoretical physics. It proposes that the universe doesn't unfold in time, but rather that what we call time is something we infer from the unfolding. In this picture, the past isn't something that was always there. It's something the present constructs, and what we perceive as the arrow of time may not point forward because of some built-in directionality, but because the statistical patterns of increasing entropy and the entanglement structure of quantum states give it the illusion of flow. This means the past might not be the foundation of the now, but rather, the now is the one writing the past into existence, retroactively crafting a memory trail of how things seem to have come to be. To grasp how such a seemingly upside-down idea could hold water, we need to zoom in on the physics of the very small and the very early. In quantum mechanics, the core equations that describe how particles evolve, like the Schrödinger equation, are time-symmetric. They don't care whether time moves forward or backward. They simply evolve wave functions based on initial conditions. Likewise, the fundamental laws of nature, as written in the language of relativity and quantum field theory, don't inherently privilege one temporal direction. So where does our experience of time come from? One clue lies in entanglement, the peculiar quantum connection between systems where the state of one can instantaneously reflect the state of another. In certain models, the growth of entanglement between subsystems can mimic what we perceive as the passage of time. In this view, time is not something imposed upon the system from outside, but something that arises when information becomes distributed in a specific way. Just as heat emerges from the chaotic motion of particles, the direction of time might emerge from the flow of quantum correlations. In the earliest moments of the universe, or in certain isolated quantum systems, this temporal structure might not exist at all. Time, in other words, may not be a constant presence, but a phase, something that turns on when the right quantum conditions are met. One of the most compelling theoretical frameworks exploring this idea is the Page-Wootters mechanism, which proposes that time evolution can arise from a timeless global quantum state when one part of the system is used as a clock to measure the rest. According to this approach, the total universe is described by a static wave function, a snapshot containing all possibilities simultaneously. But when you look at one part of it relative to another, you get the appearance of evolution. It's not that the universe moves forward in time. It's that parts of it move with respect to each other in such a way that it looks like time flows. This relative motion gives rise to the illusion of a dynamic world. It's a deeply relational view, Time exists only in comparison. And this dovetails beautifully with general relativity, which tells us that time is flexible, dependent on gravity, motion, and context. Clocks tick at different rates, depending on where and how fast they move. So why not take that a step further and ask, what if clocks don't tick at all until there's something to compare? Another doorway into emergent time comes from thermodynamics, particularly from the concept of entropy, the measure of disorder or missing information in a system in classical physics. The second law of thermodynamics says that entropy tends to increase over time, giving rise to the arrow of time. But in a fundamental theory, where time doesn't exist yet, entropy must also be emergent. Several models suggest that time's direction appears because we perceive the universe as moving from lower entropy states to higher ones. Our psychological and biological experience of time, then, is tied not to an objective flow, but to a subjective tracking of change, memory, and information loss. The past feels fixed because we retain records of it. The future feels open because we don't. But this may be nothing more than a statistical artifact. If the universe started in a very special, low entropy state, then the natural unfolding of complexity would always feel like time was flowing in one direction. Even though, from a God's eye view, no such direction truly exists. In cutting-edge research, including causal set theory, quantum gravity, and adds over CFT duality, the possibility that spacetime itself, and thus time, is not fundamental is being taken seriously in these theories. What we think of as spacetime is a coarse, grained approximation, a smoothed-out illusion that arises from deeper quantum ingredients. Just as temperature arises from molecular motion, spacetime geometry may arise from quantum entanglement patterns and probabilistic interactions. And if spacetime is emergent, time must be too. Some researchers go even further and argue that time might only exist in regions of the universe where there is enough complexity, enough separation between degrees of freedom to allow entropic flow and relational change. In this sense, the birth of time could coincide with the birth of structure, not in the abstract sense, but literally, time might not exist in the vacuum or in perfectly uniform fields, but only in systems with internal difference. This also forces a profound re-evaluation of the past. If time is emergent, then what we call the past might not be a fully defined region of the universe, stretching out behind us like a road we've walked. Instead, the past could be a construct, a projection backward from the present, assembled by the mind or by physical systems that record states, neurons, photographs, fossils. In this model, the memory of the past doesn't necessarily mean that the past objectively exists. It means that the present contains correlations and structures that make it seem as though there was a coherent sequence leading up to now. And if those correlations changed, if we had a different set of records, we'd perceive a different past. In this view, causality itself is not a primitive concept, but an emergent one, a byproduct of how information arranges itself across the evolving now. This doesn't mean that anything goes, or that memory is arbitrary. It means that the stability of the past is rooted in the structure of present information, not in some timeless film reel playing out from beginning to end. Such a perspective radically alters how we think about physics, time travel, consciousness, and even free will. If time is not a river flowing from past to future, but a phenomenon constructed from within the system, then cause and effect are not eternal laws, but patterns that emerge under the right conditions. This may help explain quantum paradoxes like superposition and entanglement, where outcomes seem to blur or reverse temporal order. It could also shed light on the puzzle of quantum measurement, why the act of observing something seems to collapse possibilities into a definite event. If before and after aren't fixed until information is distributed in a certain way, then perhaps measurement is the creation of time's direction, not its observation. And on a human level, it suggests that our experience of continuity, our narrative identity, our sense of moving forward through life, may all be artifacts of a deep computational process, that the universe performs on itself. So the next time you feel time slipping by, when you watch the sun rise, or see an old photograph, or feel the weight of a memory, consider this: what you're experiencing may not be the movement of time, but the emergence of structure. The flow you feel might be the mind stitching moments together into a line that never truly existed. The past you remember may be a holographic echo, stabilized by patterns in the present, and the future may not be waiting ahead, but arising alongside you step by step, like a melody that only forms as the notes are played. In a universe where time is not a backdrop, but a bloom of entanglement and entropy, every second is a miracle of context. A temporary structure, delicately balanced, beautifully constructed, and deeply, mysteriously alive. Emergence of time, when the past is not a prerequisite. What if time, the very thing we assume to be ever, present and constantly flowing, isn't actually fundamental at all, but something that emerges under specific conditions, something that only appears when the universe becomes complex enough to need it? What if the ticking of clocks, the aging of stars, the rhythm of your heartbeat, and the memory of yesterday are not signs of time's existence, but clues to its construction, assembled from patterns, correlations, and thermodynamic gradients, rather than built into the core of the cosmos? The idea that time is emergent, that it's not a prerequisite for existence, but a consequence of it, is one of the most radical and intriguing notions in modern theoretical physics. It proposes that the universe doesn't unfold in time, but rather that what we call time is something we infer from the unfolding. In this picture, the past isn't something that was always there. It's something the present constructs. And what we perceive as the arrow of time may not point forward because of some built-in directionality, but because the statistical patterns of increasing entropy and the entanglement structure of quantum states give it the illusion of flow. This means the past might not be the foundation of the now, but rather the now is the one writing the past into existence, retroactively crafting a memory trail of how things seem to have come to be. To grasp how such a seemingly upside-down idea could hold water, we need to zoom in on the physics of the very small and the very early. In quantum mechanics, the core equations that describe how particles evolve, like the Schrödinger equation, are time-symmetric. They don't care whether time moves forward or backward. They simply evolve wave functions based on initial conditions. Likewise, the fundamental laws of nature, as written in the language of relativity and quantum field theory, don't inherently privilege one temporal direction. So where does our experience of time come from? One clue lies in entanglement, the peculiar quantum connection between systems where the state of one can instantaneously reflect the state of another. In certain models, the growth of entanglement between subsystems can mimic what we perceive as the passage of time. In this view, time is not something imposed upon the system from outside, but something that arises when information becomes distributed in a specific way. Just as heat emerges from the chaotic motion of particles, the direction of time might emerge from the flow of quantum correlations. In the earliest moments of the universe, or in certain isolated quantum systems, this temporal structure might not exist at all. Time, in other words, may not be a constant presence, but a phase, something that turns on when the right quantum conditions are met. One of the most compelling theoretical frameworks exploring this idea is the Page-Wootters mechanism, which proposes that time evolution can arise from a timeless global quantum state when one part of the system is used as a clock to measure the rest. According to this approach, the total universe is described by a static wave function, a snapshot containing all possibilities simultaneously. But when you look at one part of it relative to another, you get the appearance of evolution. It's not that the universe moves forward in time, it's that parts of it move with respect to each other in such a way that it looks like time flows. This relative motion gives rise to the illusion of a dynamic world. It's a deeply relational view. Time exists only in comparison, and this dovetails beautifully with general relativity, which tells us that time is flexible, dependent on gravity, motion, and context. Clocks tick at different rates, depending on where and how fast they move. So why not take that a step further and ask, what if clocks don't tick at all until there's something to compare? Another doorway into emergent time comes from thermodynamics, particularly from the concept of entropy, the measure of disorder or missing information in a system, in classical physics. The second law of thermodynamics says that entropy tends to increase over time, giving rise to the arrow of time. But in a fundamental theory, where time doesn't exist yet, entropy must also be emergent. Several models suggest that time's direction appears because we perceive the universe as moving from lower entropy states to higher ones. Our psychological and biological experience of time, then, is tied not to an objective flow, but to a subjective tracking of change, memory, and information loss. The past feels fixed because we retain records of it. The future feels open because we don't.